It's amazing. They do such a fantastic job because it's the busiest airport in the world for that week.
For that week, right? And
Yes.
it's you've got what three landing zones on each runway, I think at least. And there's what three or
Yes, there's 3 on the east-west runway, that's, 27 and 9. The north-south runway, 36 and 18.
mhm,
I'm forget, I think there's 3 on that too. But yeah, they
okay,
have, colored dots
colored dots.
or squares on the runway, and so as you're coming in, you're on final, the controller will call up and tell you, "I want you to run on or land on the green dot." Green dot's a really famous one. In fact,
Right, yeah.
EAA has a show called The Green Dot. Um,
Yeah, I've listened to it. Yeah.
and so it's amazing. And then sometimes as you're going, they'll change it and want you to land longer. Say, "Okay, skip the green dot, I want you to go down to the blue dot." Or
Right.
I guess it's purple dot at the end. And so you actually have to put power back in and go a little faster.
Good evening, everybody. Welcome back to the Aviation RCNoob podcast. My name is Joe.
And I am Matt. And today we have a special pleasure an honor to speak with Leon S. Searl. A YouTuber has informed and inspired thousands regarding the efforts of dealing and the details and thought processes of going through the ultralight building process, the design and build, right? Is that correct, Leon? Welcome
You
aboard.
you got it right. Thank you very much. I'm very
Yeah, you're
pleased to be
welcome.
here.
Yeah.
We're thankful for you coming on.
Yeah, really excited to have you on. And today we're going to talk about maybe scale aerodynamics or RC versus ultralight aerodynamics.
Sure.
So we reached out. I reached out to Leon as he's kind of inspired me to really, I'll call it grok or try to fully understand how aerodynamics happen.
Well,
Yeah, so we are here to talk about RC versus ultralight aviation or aerodynamics, kind of spurred on by what you've been doing in your channel, Leon. You inspired me to pick up some of those reference books because one of the things I've been curious is, how do you design composites, right? Every time I look and I look it up, none of it made any darn sense. And then I started looking at your list of things. I always wanted to understand aerodynamics better, partly from last time Joe and I had done the airfoil uh, and lift issue way back in episode insert number here, which is like 12 or 30 or somewhere in there. He and I realized it's a deep well. It goes way down to the bottom. And so part of what I wanted to do was understand it better, along with so I picked up some of the books and I've read through most of them. I'm kind of plugging through some of that structural analysis book, which is um, it is dense with information. It is structural engineer level technical. So there's a lot in there, and there's a lot for me to really kind of get. It's one of those ones where you read through it 3 or 4 times and maybe you get it. Um, so so I'm plugging through that one. But part of what we started talking about is what I love is I'm looking at what you're doing on your channel, which is building ultralights, or at least talking about what it takes to the theory and calculations that go into making your own design of an ultralight, right? So it's not just, hey, here
Sure.
I bought a kit. We're gonna put this thing together, right? Like
Completely
there's a bunch,
different. Yeah.
right? There's a lot of those channels.
Yeah.
But what you do, and and I love watching those because I'm like, holy cow, those guys are putting together full size aircraft. This looks exactly like putting together an RC kit. I mean, in many ways. There's a lot more
Mhm.
to it. There's a lot more checks and balances that go along the way. But what I don't see anybody talking about ever is like what goes into all this stuff. And so there was a couple gaps that just didn't make any sense. And so when I watched your channel, you helped fill in those gaps because you're like, oh, this here is this, and it's this line here, and here's the number, and this is where you pull it from here, and you're worried about this part and this part. I mean, the in between is nice to know, but you really want to know these couple pieces, right? And you kind of correlated. I've looked at those aerodynamic charts. I can't tell you how many times. You're like, oh, you just put it on a roll and just look at all the charts. and, and it never made sense to me. And your channel was the first time I've really got it. Like it really genuinely made sense. It's because you went from that theoretical thing and brought it to the numbers and the charts, and then brought those numbers and the sense of it back to why you use it and how you use it, which is really cool with the formulas and then how that yields values that you're looking for, which is part of why I wanted to talk to you. And then of course this, we'll kind of go on a little bit more about what spawned this, but most of it came down to when I said, hey, have you ever built the scale model of your designs?
Right.
And then you're like, oh, that's a good question. I'm like, hey, would you want to come on and talk to us about aerodynamics and how things scale and how they don't, right? And so you've graciously took on that task for us, and I appreciate you agreeing to do that. I know it's a tough task. So, but one of the things before we get too deep is we always talk about our journey, like what have we been doing in aviation in the last couple of weeks.
Oh yeah.
And then we talk about things that are going on in our community, keep everybody up to date. And you've been part of our community for a little while, so you've seen, we try to keep pretty active.
Oh yeah, very active.
I've got small.
Your Discord is awesome, by the way. I really enjoy it.
Really?
Yes.
Good. Oh,
Thank you for that.
Yeah, I really appreciate that. Honestly, we love the guys. That's part of it's like, it's the one place I get to go and just geek out aviation.
Mm-hmm.
And there's nothing but a choir of people wanting to talk the same talk, as opposed to people like, oh my God, could you again? You still talking about airplanes, huh? Yeah, I'm still talking about airplanes. They're still capturing my imagination, right? And we have a little history of the ultralights because I thought that would be appropriate for today. We usually try to tackle a history of a plane we're doing or a plane that has been requested. One of the ones that people are like, oh man, could you talk about the whatever, insert famous or not famous plane here. And I figured, well, we're talking about ultralights. You might be able to help us understand some more of the history if you have any. I know you've been out to Oshkosh, and I know they have a pretty good, I don't know if you've been to the museum there. I know when you go, you said you went a little while back. As I understand it, it's the busiest week ever.
Oh yes.
It's right. So AirVentures, right?
If you ever get a chance to go to AirVenture at least once, I think it's worth doing because it is kind of like the airplane mecca. In fact, it's really funny. The air traffic controllers that work there, they're all volunteers. But the process to become a controller there is tough. You have to have tons of experience, and lots of controllers try to get in there, and you only get, I could be wrong about the number, but I think a total of 50 get to go there, and they work in shifts, and it's amazing. They do such a fantastic job because it's the busiest airport in the world for that week.
For that week, right? And you've got what three landing zones on each runway, I think at least. And there's what, three?
Yes, there's 3 on the east-west runway. That's 27 and 9. The north-south runway, 36 and 18.
Mm-hmm.
I forget. I think there's 3 on that too. But yeah, they have colored dots or squares on the runway. And so as you're coming in, you're on final, the controller will call up and tell you, I want you to run or land on the green dot. Green dot's a really famous one. In fact, EAA has a show called The Green Dot.
Yeah, I've listened to it. Yeah.
And so it's amazing. And then sometimes as you're going, they'll change it and want you to land longer. Say, okay, skip the green dot. I want you to go down to the blue dot. Or I guess it's purple dot at the end. And so you actually have to put power back in and go a little, and just floating up along the top of the runway and then go down to the next dot. Because it's so busy, you'll have a fast plane coming up behind you perhaps, and you'll say, okay, the slow plane go all the way down the end of the runway so the fast plane can land. So yeah, it's amazing. They do such a great job.
Right, and then they're bringing in anywhere from ultralights, right, to full scale fast, twin birds that have got pretty good,
Uh,
pretty long needs for landing distance. Maybe not
well,
like a 737, but
so the ultralights have their own runway, dedicated runway, and they have certain
okay,
times of the day that they can come in and fly. And there's a time in the morning and a time in the evening. Um, most of
okay,
the warbirds and quite a few of the private airplanes land on the east-west runway. Um, and then some of the faster ones will have to land on north-south runway. But lots of
okay.
private airplanes also land on north-south
Yeah.
runway.
So Leon, you were saying that we were talking about the history of ultralights, and I know that in Oshkosh, as you were talking, that they have I guess they have one of the gliders, one of the early ultralights is in their museum because they've got a museum there.
Yes.
Um, so I think which is one of the ones from John Moody had a.
Yeah, I think it's the
Yeah.
John Movie's Easy Riser. It's
Uh,
the
I
it's the it's the like his very first version of the uh before the MXs. The
yeah,
Quicksilver, it's a biplane hang glider that you hang by
yeah,
your armpits on it. At least the first version was,
yeah. The
yeah.
first version, I think, and they
Yeah.
ended up quickly converting it to a trike
Yeah,
for the police use,
yeah.
which is what's up there, I think.
But yeah, that was
Um,
back in the, if I remember right, the early '80s, something like that.
yeah, we'll get
It was,
into exactly when that is, and
yeah,
yeah, it's mid 70s actually,
mid-70s. Okay.
and late
Yeah.
60s was some of the earliest, but yeah, it really kind of came in its heyday in the 80s. But and then we'll get into the main topic. Obviously, you and I will talk. All three of us will sit down and try to figure out what the heck. One, we'll learn about you and kind of where you came from, where you're going, and what the YouTube channel is more about. That if I miss some things, and then we'll get into this topic of scale aerodynamics. So
Let's do it.
let's do it. So let's talk about what we've been doing the last couple weeks in aviation. Usually we ask our guests to go first. If you'd like to do the honors,
Oh, okay.
you're welcome to. If not, you can
How far back you want to go? Month or just a week?
just a couple weeks.
Okay. For the most part, I've been working on design for the nose rib for the Universe 4 ultralight airplane. And
What does that stand for?
oh, well, UWS is basically ultralight airplane workshop. It's just
Okay,
I didn't want to use UAW because that's already been used.
got it. I
Um,
just want to know because I mean, if
yeah,
you're just hearing the numbers for the first time or the name,
yeah. And it's
there I
supposed to
know
be
you have
it's
a
the
reason.
fourth design I've thought about doing. I started on a UWS 1, which was an all composite airplane with
Hmm.
2 electric motors, but I paused design on that one for 2 reasons. One is the composites were costing me a lot of money because I
Yeah,
was
they are
doing
expensive.
carbon fiber and PVC foam, and
Okay,
so that was costing a lot. And the
yeah.
other one was that I didn't think that batteries were far enough long for what I wanted to do. I mean, you can get up for about 20 to 40 minutes flight, but I wanted to
Okay.
be able to do longer flights. So
Okay.
batteries,
Yeah, I was gonna say how yeah, what was your mission on that? Is it for
yeah.
you were aiming
So
for an
the
hour?
the UBS one again was more of a longer flight because it was going to be pretty low drag airplane, kind of like the UBS 4. Mission for
Okay.
that is also a fairly long flight, so I want to have low drag and low fuel consumption. So yeah.
Okay.
And then I had a couple other designs I thought about doing, and I decided to actually switch over to a aluminum airplane. So that's the UBS 4.
Okay. Well, good. I know you were also so what kind of things were you working on? I know you had kind of hammered out one design and had tested it earlier, probably about a month and a half ago, I think,
Mm,
according to your channel.
right. I didn't
Um,
bring that was a cantilever style rib.
okay.
Um, so I wanted to try both cantilever and truss style. I wanted to try to see what the weight difference was because typically a cantilever style, just about anything will be heavier than a truss style.
Okay.
Um, but I wanted to try to test it out, and so I did a little bit of testing on the rounded parts that would be inside, and to figure out
Mm-hmm.
what radius I needed to have and how wide the flange needed to be. So I did some
Right.
individual parts there and figured out I wanted about a 3-inch radius with a half-inch flange. So at least I
Okay.
figured that part out. And then I said, I don't know how to do the analysis on this. I could have done like a finite element analysis on it. But
Yeah.
I decided, let's just get out in the shop and build something because I wanted to get back out there and do something.
Right.
So I
Good
just
old
took
empirical testing.
so I took, I shouldn't say it's a wild guess. I knew that I needed to have the flange along the top and bottom of the airfoil be
Mhm.
thick near the not the root, near the spar, and then get thinner as it went toward the nose. I
Right.
knew I needed to do that because you have to do that with cantilevers. If your flanges on the top are the same dimension, then you have to make it wider as you get closer to your base. The
Mhm.
web has to be wider. So I took a pretty good guess at that, and it actually turned out great. I used steel rebar for weights and took the
That's
airfoil and turned it upside down so that weight would be pulling in the correct direction for the airfoil.
as
Because,
if it were lift.
so
Right.
right side up would be lift, so it turned upside down with weight, still pulling the correct direction on the airfoil. Um, and it amazingly worked great. So at that time, I had the gross weight for the airplane being 517 pounds. And so, with the 14-inch spacing of the ribs near the root of the wing, I had to have about 76 pounds for 3.8 G loading. And so I put that on there, and it looked great. I didn't see any unusual bending. I thought, well, let's go ahead and go up to the 1.5 safety factor. And that took me up to about 112 pounds of load. Oh, I think it was 109. I ended up putting 112 on it. And when I finally got up to 112, it had not failed yet, not completely, but it had permanently deformed the rib, which is okay. The FAA regulations, now I'm not building to those regulations, at least I don't need to, but I'm using the old FAA regulations as the guide for like
Yeah.
load limits and things like that.
Yeah.
Try
I
to
mean,
build a safe airplane.
I was gonna say it tends to be
Yeah.
a pretty safe,
Yes.
safe way to go because you're looking at like, okay, this is it allows for the unknowns. Allows at least for a little gap of the unknown so that it's over designed.
Yes.
You'd rather get to the problem, get to the ground, and realize that that hole is elongated or something is a little overstressed but
Yeah.
didn't fail,
Yeah.
as opposed to having a failure midair, and obviously
Exactly.
that
So
could
that's what the
potentially be
regulations.
far more.
Yeah,
Yeah,
exactly. That's what the regulations say. So
yeah,
I'm designing the
good.
3.8 G. So I should be able to load up the airplane to 3.8 Gs, and it should come back to its normal position without any permanent damage, without any permanent deflections or something deformed. But
Okay,
if you go above that, up to an additional, not additional, but multiplied by 1.5 more, um, then it's okay if it gets deformed but doesn't fail.
mm-hmm.
So
Right, yeah, because it'll keep you in the air, right?
yeah.
Good, good. Well, that sounds
So
like it was
so
busy.
so I was very happy about that
The
cantilever
test.
style rib. So and the weight was about 72 grams. So then I designed a truss style rib,
Okay.
and
Which you would think
I
would be lighter,
it
technically.
should be lighter.
Should
Now when
be,
I
right.
finally
It saves
I
you what? An ounce on each rib, which in the end of it ends up saving like 3 pounds, or
okay,
what kind of
well
weight what kind of weight shaving are we looking at differential wise?
well it turned out that it's about the same weight, at least the way
Oh,
I
okay.
designed it.
Okay.
Um, and let's see, I got the form cut out earlier in the week, and I actually just formed it today, or at least I took my first attempt at forming it. So actually,
Okay.
this is it.
Ooh. Now, is that
And
with the new hydroforming
this is with the
method?
hydroforming, yeah. So now this is, I
Hubba
didn't do
hubba.
it the way I eventually want to do it because this is
Yeah.
about 18 inches, and my foam or rubber is 12 by 12.
Okay.
So I
Okay.
had to
Right.
work my way around and gradually put more and more pressure as I worked my way around the rib. But it, for the most part, turned out pretty good. Um, I need to make a few changes in how I do fluting around the edges here because I only did one flute between rivets here, and I need to do two. So, but for the most part, it worked pretty good. But what's
Okay.
nice is I increased the gross weight of the airplane to 580 pounds, and I did that while I was at AirVenture. Um, and so I'm pretty sure the old cantilever rib could not handle the increased gross weight. So the, what is it, 80, 87 pounds, I think, is what the rib has to carry in addition to the safety factor. And so I have a feeling would have had to redesign the cantilever rib. I don't think I have to redesign this. I think it's going to work great. So 72
Okay.
grams for this. That's
That's
not too bad.
yeah.
Now the question is, will it work? I'm pretty sure it'll work with a normal load. So the load pulling up like this. But what if you're doing upside down? In that case, it's 1.5 Gs, and you're pulling like this. Well, this is going to be in compression in that condition, and
both of
it
those
may
numbers.
fold. In tension, in this way, I think it'll work great. But in compression in this way, I don't know. We'll have to find out.
At 1.5, it might hold up.
It might, yeah. I'm hoping it will.
You're not looking at You're not looking at 3.8. You're looking at 1.5.
Are you looking to go inverted at some point?
Well, you have to handle an inverted load. You're required to do that according to FAA.
Right. If something goes wrong and you end up basically partially inverting, if you go over and maybe a weird spin or a wind grabs a wing and flips your plane over, because a gust might do that. Not that it will happen very often at all, but it is possible.
Those are possible. I think the more likely condition is you're going to hit a really strong downdraft.
Yeah. And
I was thinking about when you were talking about your load testing and factors of safety, like if you had caught a downdraft and then while in that came out of it immediately into an updraft, what sort of pressures was I going to put? But I didn't even think about flying normal and then suddenly hitting a downdraft.
Right. Yeah. Oh, now there's another thing, and I've talked about in some of my previous videos. There is something called a maneuvering speed, VA, where if you're flying at or below that maneuvering speed, it really doesn't matter what kind of gust you hit, the wing will stall before it breaks.
I gotcha, yeah. Because sudden differential will cause
because you won't get enough lift.
Right.
The slower you fly, the less load the wing can make. And so it'll stall if the angle of attack gets too big before it gets too big a load. So if you're flying below VA, and I've designed it so VA is at 3.8 Gs, so that's my low limit at VA. But if I'm below VA, then, well, for example, let's say we're at stall. The maximum load you can carry at stall is going to be roughly 1 G, because it'll stall before anything happens. So the slower you go, the lower that stall speed gets, and the lower lift your wing will have.
Okay.
Nice. See, this is why we have them on, Joe.
I'm just over here pretending to understand lift.
Yeah. No, and that's hopefully we can kind of get a little bit, I don't know, but deeper, but maybe get to a better understanding here today. That's kind of part of why we wanted to have you on, and because just listening to your videos, I'm like, okay, this guy gets it. Like you get it. Not only do you get it, but you get the technical aspect. You can get the how to calculate it, but you can also you put it in terms that for the first time I was like, oh, okay, I get that. Like, oh no, this is stickiness. This is whatever. When you're talking about the Coanda factor. And some of the viscosities and all that kind of stuff. I'm like, oh yeah, I never really heard it described like that. Of course, that's what it is, but cool.
So one last thing, just if that's okay.
Yeah, what else have you been working on?
So in order to test this one, I'm going to do something different. Instead of putting weights on it, I'm going to use a whipple tree or whiffle tree, either one you want to call it.
What is that?
So that's where you have a series of arms that come up. So I'm going to have wires that come up to, like, let's say between these two front rivets, there's going to be a couple wires that come up to a bar, and they're going to attach to each side of that bar. And I'm going to do that for each pair of rivets coming back here. And then those two bars here will connect to another bar. And then two more back here connect to another bar. So you keep going up until you get one bar left. And if you set your connections on the next bar up in the right spot, you'll actually put the correct load on the rib. So we want more load up here at the nose than we do back here.
Okay.
So
why would you want more load up there? Is that that's because the aerodynamic when we look at the Navier-Stokes equation, when you look at all those individual arrows, right? Most of it's right there at that point that you're pointing at right now.
So the pressure when you're up at a high angle of attack, you got a massive amount of pressure up here at the nose, and then it falls off at kind of a triangular shape back to about the 25% chord. And that's a much shallower angle back to the trailing edge then. But you're going to have lots of load up here
Yeah, all
endless
your
load
load
back
is
here.
in the. I never even
Yeah.
thought about that. That
Yeah.
makes absolute perfect sense. Okay, so you build that tree so that it's pulling on all those points to mimic that same load condition.
Correct.
Perfect.
Yep.
And then you can just add whatever weight until you
Yep.
say,
I
"Hey,
just
I've reached."
I put a hydraulic jack on it and just keep
Mhm.
cranking on it until I get up to. No, I have a load cell so I can see how much the
Right.
total load is. Yeah.
Right.
So
So you know that if you met your 3.8 and
Yep.
now you don't have to document all this stuff like you do in a full scale
Not for an
aircraft.
ultralight. No, I can do whatever I
So
want. Yeah.
yeah. Well, you want to make sure you're safe. So
I do.
they,
Yeah, absolutely.
yeah, having that in your back pocket so that way somebody's like, "What did you do?" It's like, "This is exactly what I did."
Yeah.
But
This
that's when you'll
whole.
see a lot of videos on people building their own kit aircraft. It's
Mhm.
because when you're making kits, sport or kit or experimental, you have to show that you've done all these tests and when you've verified that it's performing to the specs that have been set forth, right?
Well,
That's typically why you see a lot of it's because I see a lot of build videos for kit
yes.
airplanes and things like that. And
Yes.
I get the impression that that's the reason. You can make a video log, you make a blog, you can take a bunch of photos, but boy, it sure is easy to just turn on the camera, do the things, and go, "Oh, hey, we're going to do this test now." You record the test. It's now officially a
Yeah,
log. If anybody ever needs to look at it, it's there, right?
that's true.
Yeah. Okay.
So that's what I've been doing.
Awesome. Sounds fun. Actually, sounds like a
I really enjoyed it. That was the first time I ever done hydroforming, and I learned a lot from it. So one of the reasons I only did the 12 by 12 rubber is that it's super expensive,
yeah.
and because I got two 1 inch pieces, and they're like 200 some bucks each.
Oof.
Um,
Yeah. Yikes.
now I want, so I decided
It's not a standard rubber though, right? It's not like you just went out and grabbed like a
it's a
rubber at the
it's a
rubber shop.
neoprene. Yeah, I
Okay.
got it from McMaster Car.
Oh, okay.
Yeah.
The rubber shop it is.
Yeah, but
Nice.
I wanted to make sure I could get the bends that I wanted on here, and I came
Right.
pretty darn close. I didn't put all the pressure on it that I might have been able to, but my press was making some noises, so I decided I was gonna putting more pressure on it.
Wow.
Um, but what I'm going to do is I'm pretty happy with this, so I want to proceed. So I'm going to get some bigger pieces of rubber. I'm going to get 18 inches by 36 inches
Okay.
so that I can make the main rib too. And what's
Okay.
better is to press all of it all at once instead of
Right.
moving around like I did.
Yeah, because you can
Because
create local stresses in there that you wouldn't normally have
yeah,
otherwise.
you can do. You got to be careful because you don't want to stretch it. If I did a full press on one part of it and it bent a flange down, but right next to it the flange is still up, you've
Yeah.
really stretched that
Yeah.
aluminum right there and it's liable to crack. So you want to try to stretch a little bit at a time. So it took a long time of doing a little here and then a little here and then a little here. It's annoying. So I wouldn't want to really do it for like 20 ribs.
So if you don't know, if you're a listener, you listen to this and you go, I don't what the heck is hydroforming? It is basically when you have a mold and you have a material and then you put a piece of rubber on it, once that rubber hits a certain pressure, it effectively liquefies temporarily during that pressure. It pushes the material into the form and it fills it all out like a liquid, right? Like a pressurized liquid. And then when you release it, the rubber goes back to being a solid in the original shape it was. Now your material is deformed per the mold, and you are ready to take that piece out and use the mold again. And the rubber is just like it was when you first started. Now, I think it degrades over time eventually, but
Oh yeah.
the rubber is quite reusable as I understand it. And that's what hydroforming is. So you can basically, if you have one rib that you need to make 36 copies of or 1,000, right? Like you go right ahead. And that is one way to do it in a kind of we'll call it the simplified version is just a quick stamp, but it's not
Yeah.
quick.
Yeah.
There's nothing terribly quick about it per se. But if you have the single piece of rubber and you have a hydraulic press that can exert enough pressure to do that, it's a I'll call it a unique property of rubber where once it reaches a certain pressure, it does this magic turning to liquid temporarily. Maybe it's not quite liquid, but it's
I
has
would
a
just say that
liquid-like properties.
it kind of flows is probably what I would say.
There you go. Yeah, yeah. But it's not completely but it will return to its original shape, which
Yes.
is crazy. So,
Unless you do something crazy, which I don't have enough power to do that.
okay. Nice. Well,
Yeah.
anyway, just I wanted to be because if you've never seen it, go look on YouTube. There's a bunch of videos on it. It's the craziest
Yeah.
craziest thing to see. It's really cool.
Well, there'll be another video on it next week.
All right. Well, good. I'm looking forward to it. Joe, what about you? What have you been up to? Thanks, Leon.
Sure.
Well, not a whole lot. Still continuing on with some work projects, and I know it comes up a lot. I have tinkered a little bit with the 3D printer, got a little bit of cleanup done in here. Did some cleaning up in the garage so that I've kind of got a little more room to work. Got some more work to do out there. Played a bit with the LED lights, still having trouble getting them to communicate right. And honestly, a lot of my time in the last month and a half has been playing a game with my wife. And
Yep, Baldur's Gate.
Yep. And we finally beat it.
Nice.
Apparently, there's a relatively small percentage of people who have actually beaten it that own the game. So apparently, that's an achievement. But we beat it, so things on that side are going to be done. Not every spare moment is going to be doing that.
Okay.
And I'll be able to start diving into projects again. I've got to start putting wings together for this giant wonder.
Well, at least a spar. Spar is the first order of business, right?
Yeah, and you sent me the files for that somewhere, so I'll print them off and get going.
I tell you, it's easy, and it is, but it's also you've been
I
there
was
while it's being
there.
constructed.
Yeah,
it's not entirely easy.
It's going to be interesting, but now's about the time when I need to start, or I will end up running out of time. Going at the rate that I go.
Yeah, fair. No, at least you know you. That's kind of like where I know me, and if I don't do a certain thing by a certain time, I'm going to start being in trouble.
Mm-hmm.
So it's good, dude. That's awesome. Well, it sounds like you've got your spaces getting close.
Getting there.
Which means that you'll be able to, I guess, get to it when you feel like getting to it, which is always a good feeling, right?
It's
just with anything. Like you're like, I want to do a thing, and you're like, oh, I got to clear everything off first. You're like, well, there goes that day.
Things for the first time in a long time. Just I'm at a life point right now where I'm not feeling pressure of there's a million things that I have to do. Don't get me wrong, I got a lot going on because I'm still doing Monday Night D&D, and I'm still working with a church. I'm still doing things with work, but I'm kind of at a point right now where I don't feel like if I don't work on something that my world's going to fall behind and things are going to fall apart.
Mm-hmm.
And there's a certain peace that's coming with that I'm enjoying.
Well, good.
I can tinker on things as I have the interest and the desire to tinker on them. And it's kind of nice.
Yeah, it is a nice feeling. When you get to that, you have that moment for a little while. You're like, oh, there it is. Or you can be retired like Leon. Leon, you're retired, right? You get like, oh, I got all the time I got all the time in the world.
Except for all the stuff my wife makes me do now that I'm retired.
Yeah. I can understand that. Get a day off and
it's already filled.
Yep.
Sometimes. Look at that. Rachel's not bad.
No, she's good.
Yeah. What about you? What you been up to?
Well, mostly I've been I skinned the landing surface of the aircraft carrier project. So the upper two surfaces of the wing each are 20 by 70 70. That's about 6 feet, right? 72 inches is what I think it ended up being. And so the whole thing will be 40 inches wide, which is 3.5 feet by 70 inches, which is 6. So 3 by 6 is the landing surface, and then I have was it 7.5? So 90 inches by 10 inches, 12 inches of wing behind me. So I've got the main wing. I'll call it the main lifting wing. The rear wing is ready. So that one gets mounted at 3 degrees. And then there's the canard wing, which which I have ready. I was working on finishing up the spar. Because I'm going to put the motors in the front. I started thinking about where I wanted to put the motors. And
Okay.
originally I'm like, I'm going to put them in the middle, right? Like I'm going to put them on the main lifting wings, and they're going to be on either outboard side, right? And I'm like, well, if I have them in the front, I don't know if this is good or bad, but I have them in the front. When you land on the aircraft carrier, it's only when you really miss do you risk hitting the blades, right?
Right.
So if you succeed in landing where you're supposed to land or close to it, you have a good chance of just landing there. Part of me goes back and forth, right? Like if they're at the rear of the plane as pushers, then if you're on the deck, you don't have anything but just regular airflow on the
Hmm.
deck. You don't have any turbulent flow from the props potentially.
Right.
But if they're in the front, but then you have an obstruction in the back, right? If you're coming into land, you've got these high power prop flows right there. Now, if they're in the front of this 7-foot long aircraft carrier or 6-foot long, you may have lower prop wash and maybe a little bit turbulent, but it may not be as bad to land. I don't know. I'll find out probably the hard way. But that is honestly some of the experiments. And honestly, I think one of the questions I had for you, Leon, maybe
Yes.
as an outside thing, is does OpenVSP have the capability to take like an STL or some sort of 3D file, or do I have to remake my model
Mm,
there to be able to put in faux props to see where the turbulent flow impacts on the landing surface? Because
right.
my thought is if I know where that's going to be, it'll inform my choice a little bit better as to where I want the props to end up.
On
It,
that, uh, I think people have used STL to at least do fuselage input. I don't know
mhm.
about the whole plane because
Yeah, the wings
OpenVSP
you want to have the actual
OpenVSP
file.
wants the various parts of the airplane to be a type. Like wings should be a wing type, and the tail servers and
Uh-huh.
rudders. Fuselage
Okay.
can be just about several different kinds of type, but wings it wants to be wings, so that it knows that it should
You
do a wing analysis on it, and and a
okay.
different analysis on the
And you have
fuselage.
to ID the parameters of the wing itself and not just like, hey,
Right,
I
right.
want this shape, whatever this random shape is I put in there.
It
Okay.
can output an STL file though.
Well, that's good to know. All right. Okay, well
Now,
good.
this
Good.
is still a 1/3 mock-up you're working on?
It's a 1/3 mock. Well, again, it may not be strict 1/3, but that's my goal. Right? My whole hope is that it'll be like a 20-foot by I don't know, 8-foot,
Landing
landing
pad.
surface.
Wow.
My thought is if I'm going at 20 miles an hour and a plane can slow down to about 40, the differential 20 miles an hour might be able to land on a 20-foot runway. A scale RC, because some of those can go pretty
We're
shallow,
gonna have
right?
hooks and catch wires.
Yeah, I was thinking about it. Yeah, actually, I have a couple of ideas for that, right?
I
I
think
have a
the
couple.
leading idea that he and I last had was Velcro.
Well, right.
Oh,
I'm not. Look, I'm thinking all of the above, but that's neither here nor there. So we got a couple of ideas rolling around. First thing is to get the thing built, right, and try a bunch of different things. I may end up putting a sheet of Depron or a sheet of thin styrofoam as a covering layer on top if this film doesn't look like it's going to hold up at all, which it might not. I mean, it's lightweight, so it might not hold up to durable, landings. But I'll find that out in the hard, not a big deal. But I'm almost at that point, though. I've put a couple bracing. That's the other thing is that front wing because I'm going to put the motor load on it. I've made sure that that's fully trussed. I don't have an actual spar like a metal spar or anything like that, but I figured I'd just, you know, see the structure of the foam. I know I'm going to put in the full size one. I'm going to put, broom handles. That setup that I had last time, which I thought was pretty, like actually more than pretty sturdy. I mean, we were doing full acrobatics at a 10-foot wing load on that on our Noob Wonder, right? So we were generally having a good old time with it. So I'm going to use that same. I want to keep that same design methodology because it worked. Um, I'm just trying to figure out how I want to do it in this specifically. So anyway, I've got that front one. It's all trussed up, so it's ready to just put some motors on as I cover it and see what I'm going to do with it from there. So I was hoping to have it done today, but things turned sideways and other things took priority. Kids have science projects they got to take care of, so they need help sometimes. So it was all hands on deck for that.
It's fun when they put that off to the last minute.
And he did pretty good for the most part. But kids don't really realize, like, oh, I need to do this, and don't forget about that. And you're going to want pictures in there, aren't you? Well, it's going to take at least like 20 minutes to get those pictures from one thing to the next into a format, printed, cut, pasted, labeled, etc. Like, it doesn't take like 2 seconds. It could.
Oh, I speak from experience of being the kid that put it off to the last minute.
Oh, me too. Yeah, no, I know.
Quit making the same mistakes we made.
I know, right? Please don't. No, but generally, my youngest is really good about that stuff. He did pretty good this time. It was better than last. He has just, again, he could submit it like it is, and it would meet the requirements, but it's not as he wants it. So he's working on that. So yeah, but mostly it's been working on this thing. On and off, and kind of looking at how I want to shift a couple things in my shop. I pulled out the HD goggle add-on, and started looking at that because I want to get that set up as my main driver for the aircraft carrier. Like, I want to use that to see out of, and then I have a 3-switch analog that I was going to use for just generally for ancillary stuff. So for launching and landing and bomb sight or whatever the heck I deem fun. So yeah. Anyway, so yeah, that's about it. That's not terribly much, but it's working with the community. We went had a build night recently, so got to hang out with some folks and talk some more about different things. All airplane related. A lot of fun.
Well, speaking of community, we've got you continue to host the Build Jewelry event every February.
Yep, and so we're 2 weeks away from that, from the start. And if you want to join in, you can have your kits. You can basically have whatever planes you want, cut them all out, all the pieces out. Just don't start building them. So you can have them prepped as if they were a speed build kit. Same with 3D printing. If you have a 3D printer, print a 3D plane, have all the pieces ready, but don't have it assembled. And then
Just
come February 1st at 1 in the morning or whatever, 12 in the morning, start gluing, and good luck. and hopefully by the end of February, you have 4 planes built and 4 planes flown, with an extra week to get some videos up, because I know sometimes it's not always the quickest thing to do. So I know a lot of people who join in end up being on the 28th at the last minute. They can go out and try to fly what they can, to get some last minute footage. So try to give that week leeway. It happens.
But like you said, so long as people have fun with it, and whether they make it or not, hey, you're further along than you were, and you got more to fly.
Right. And if nothing else, you've picked out 4 planes you want to build, right? You have them kind of selected. If you pulled together the plans and all that stuff, at least it's ready. If you cut them out, now you've got a kit ready whenever you're ready to build more. Or if you have it built, but you haven't flown it, well, now you're ready to give it a maiden. And that way, when, a couple months later, when you're ready to bring it out to the field and fly, when the weather gets a little bit better, you have a couple in the back pocket to go and have fun with, right?
Yep. And then to help encourage people and then just have fun, it looks like you're planning to hold build nights every Friday night in February.
Yeah. I'm okay. I can't say it's going to be dedicated for certain, but at least once every weekend, I will be on that build channel building stuff. I know me, and I have plenty to build. And I know that everybody else in that challenge will be probably building. I mean, the only way you're going to get it done is if you actually sit down and build almost every week. So this is a way to encourage it and also get together with all the people doing it. But if you are not joined in, and I encourage you to do so, but if you want to still join in and talk with us and chat airplanes and build along with us at your own bench, and you're not in the challenge, it's okay. You can join in. We'll be in the build, the build channel.
Discord party in the doobly doo. Thank you, Matt.
Yeah, we'll have a link there. Yep. Yeah, that's it.
All right. Ready to talk about history of ultralights real quick? And then
I am ready. John, I don't know if you've moved any slides ahead or anything like that, but
I am trying. I seem to be stuck,
all right.
but yeah, go ahead.
That's fine. Well, anyway, I'll keep going and you'll eventually, I guess, catch up. I didn't put any pictures of these ultralights, but basically, when the British and French gliding enthusiasts tested gliders, they test them propelled by small engines in 1922. They effectively created a new low-cost ultralight airplane. The idea all but disappeared until a few hang glider pilots began experimenting with small engines once again, and they called those glide extenders during the late 1960s. Their work did not reach a wide audience until John Moody installed a 12.5 horsepower engine on his Icarus II hang glider in 1975. The following August, as thousands of fellow flyer enthusiasts watched Moody he ignited the modern ultralight movement in America by demonstrating running takeoffs and landings from level ground at the Experimental Aircraft Association Flying Convention in Oshkosh. That's the Air Ventures. That's what it ended up becoming. And on display is in their museum is, I believe, the police glider. And so a lot of what that took off from there is in certain areas of the country, it's very tough to police some of the parks and some of the areas because they're kind of long ranging and hard to get to. So a lot of police agencies had considered using a laser, for example. I think we have a picture of that in our notes here, and yeah, the Icarus 2, or there's another a couple other. They made them very easy to fly, and then basically police would take off, and they would surveil the area and make sure that there wasn't any people doing things they shouldn't be doing, I guess. One of the difficulties why that didn't really continue was that they needed there weren't a lot of really great places to land. Part of the reason why they can't go and surveil those parks terribly easily is because there's not a lot. So when something happened and they had to make an emergency landing, it was really dangerous. So after a short while, the police kind of nixed. They loved the idea, and they thought it was actually really smart if there was only a way to kind of make it a little safer. And I think today's day and age, I suppose with a powered parachute or with a parachute contingency, I wouldn't say it makes it safer, but it allows you to land without as much danger, I suppose. Maybe Leon, you could talk to that, but
You can certainly land in a shorter distance. So yeah, you can set down in places you wouldn't be able to with a regular ultralight, but
mm,
taking off again would be pretty tough.
so is that kind of like those parachutes? Are they kind of almost like what are those professional skydiver shoots where you can control kind of as you're coming in?
There
So
is a
it's
lot
not
of similarity, yeah, because they're self-filling. They have use ram air to inflate and hold their
mhm,
shape. So yeah, and you can pull back on the trailing edge and really
okay.
slow the wing down, and yeah,
Yeah.
absolutely.
Okay. All right. Good. Yeah, I wasn't sure how if they were just like a dumb, we'll call it paratrooper kind of parachute.
It
And I say that as in like the traditional thing we always think of, where there's this big, just mushroom shaped dome, and that's pretty
Right,
much you just come
right.
down to the ground safe. Or is it more one where you actually control kind of how you get in? You
Yeah,
know.
you can do a lot of they can do some amazing stuff with those. It's pretty phenomenal.
Yeah. I didn't even get into it, but I know, and I don't know that you're necessarily going to need to cover a whole lot of it. But there are a lot of different there's like different levels, right? There's like there's ultralight, there's microlight, there's weight shift, and then there's paraglide, right? They all kind of meet in this unregulated category, right? Which is part 103.
Well,
I don't know if part 103 really, that's not really in, I don't know. Maybe you can
okay,
help us
well,
understand.
microlight isn't usually a term used here in the alt-light stuff. Um, a lot of foreign countries use microlight to mean a specific thing, but a legal ultralight in the United States falls under the Federal Aviation Regulations Part 103. And so if you
Hmm.
meet the regulations for Part 103, you're unregulated.
Okay.
And that allows you to fly in airspace that is E, most of E, and all of G. if you're familiar with the airspace terminology, A, B, C,
A little
D,
bit,
G,
yeah.
F. Yeah.
For those listeners who don't know terribly well, G is kind of like anywhere that isn't
G is
any other
unregulated.
designation,
Yeah.
right? Like
Yeah.
everywhere else, you know.
Yeah. Yeah.
So if it's not a towered airspace, right? So that's A, B. Well, that's B, C, D.
Well,
Are
A
towered
is
airspaces, right?
high altitude,
Right,
above
that's
what,
high altitude.
18.5, I think.
Right, up,
B is your major airports,
right.
and it's an upside down wedding cake shape. So it's
Yep.
small near the bottom, and then it gets a little bit bigger, and there's another circle, and then it gets a little bit bigger. I forget what the height is on that. I think some of them go up to around 8,000 feet.
Yeah.
Or maybe it's
Yeah.
10. I forget now. I haven't
It
looked at
depends.
the A. I never look at those because I don't have to deal with them.
You don't have to do it. You just have to keep
S-
under them, right?
C is your kind of regional airports.
Mm-hmm.
D is your small towered airports.
Mm-hmm.
E is typically untowered airport. And that's about it. And then, of course,
Okay,
E,
yeah.
or let's see, E airspace is it's hard to kind of give a general explanation, but it's outside of A, B, C, or D.
If it's none of the above, then
Yeah,
it's G.
yeah.
It's
Well,
pretty
then
much
it
out.
well,
Not
it's
exactly.
probably E. The only place you'll usually find G is out west, where there's nothing around at all. That's usually where G is going to be.
Okay.
And if you want to learn more about some of that, go take your trust test, like we all should have.
Good point. Yeah,
Yep.
because you guys need to know those things too. Yeah.
Well, we're supposed to know those things.
You're
that's
supposed
for
to know
sure.
them. Yeah.
Yeah. And then if we're going to earn any money doing it, we need our Part
Oh, you
107,
have to
which
pass a test
you
to do
have
that.
to
Yeah.
pass the test. And then and that's basically I'll call it a pilot test light. They kind of take some of the pieces out, but there's a lot more in there that they don't talk about plane maneuvering, but they sure do talk about not just looking at air charts and understanding how those all work, but also understanding weather patterns and all that kind of stuff. And I'm like, have you ever flown one of these? You don't. Anyway, whatever. Okay, so we need to know those things. Got it.
Okay, so
but anyways,
so backing up to Part 103, let's kind of talk about what that actually is.
Okay.
Because you're right that there are that can actually even have helicopters that meet Part 103. There's something called Mosquito does. Hang gliders, like you said, paragliders and powered parachutes can be under there if they meet certain requirements. And then, of course, we have the the 3-axis control. Looks like a regular airplane type of ultralights too. So, single seat. You cannot have more than one seat.
Right.
There for a long time, you could have 2 seats if you had a training exemption, but the FAA got rid of that. It's gone.
They did. I wasn't because I've seen a number of ultralights that were 2-seaters, and again, they were designed to be trainers. So I mean, you got to learn how to fly somewhere.
Now they're not ultralights.
Okay.
So that's something that kind of bugs me about reporters. They'll say something's an ultralight because it looks like an ultralight, but if it's got 2 seats, it's not an ultralight.
Well, they do the same thing to drones, so don't worry about it.
Oh yeah, I think you're right. Okay, so it can only have 1 seat, and that kind of brings up the kind of one of the themes behind the Part 103 is they kind of decided if you want to go out and put yourself in danger, that's fine. You just can't put anyone else in danger. So that's one of the reasons for 1 seat.
Gotcha.
The empty weight has to be less than 254 pounds. That's for
Okay.
if it's powered. If it's unpowered, it's, oh gosh, I hate to say, I think it's around 140 pounds, 150, somewhere around in there.
Yeah, I think so.
It has to stall at 24 knots or less. The maximum level flight cruise speed, so with throttle all the way pushed in, cannot exceed 55 knots.
Right, which is what, like 65
62,
miles an hour?
about 62, yeah, 62 and a half, something like that, 63, yeah. And by the way, the 24 knot stall speed's around 28 mile per hour. And that's really the major part of it. You get an exemption of 24 pounds if you want to put a parachute on there. So that parachute then would not be included in the empty weight.
Right. So you could have a heavier craft, but again, it would have to have the parachute. So
yeah, now
up to 24 pounds.
there's an all composite airplane called the Firefly, and they worked around the issues because you get a 30-pound allowance if you have a floating hull.
Oh,
Yes.
Floating hull.
Yes. So basically a seaplane
right.
ultralight.
Oh,
Yeah.
okay, yeah.
Yeah.
Okay, gotcha. Right. If it has floats, you get an extra weight allowance.
Yeah, you get a weight allowance for floats.
Nice.
Which okay. It's kind of cool for those guys who want to land on water. But they
Look, if I lived on a lake,
it's,
that'd be a
it's
winner chicken dinner.
every time I've seen the Firefly fly, it's never been on water. It lands on land.
Right.
hey,
So,
an extra 30
Anyway,
pounds.
it's they actually the FAA has signed off on it, so it worked. So good for them.
right.
Also, now we have a lot of the same cloud restrictions that regular airplanes do in Class E airspace.
Right.
We have a regulation that's similar to other airplanes where we have to be it's either 400 or 500 feet away from buildings, people,
Yep.
or structures.
Right. Yep. And RC has to be within that envelope if we're going to go any higher.
Yeah, I know.
So we can go up along buildings, right? And up and above and around as long as we're within that 400 feet limit. Where you're like, no, you can't get anywhere closer. And that's,
now
I guess, the way they keep.
there is an exception though. Is as long as you're landing and taking off, there's an exception.
Sure.
You can be closer. So
yeah, just I hope so because there's a lot of buildings right near those airstrips.
Yeah,
right?
exactly. So that's pretty much what makes an ultralight.
Well, good. Well, that's good to know because I don't think everybody when we hear about it, and unless you're really paying too close attention, our limits are 55 pounds unless you want to get a special weight waiver and you get an extra special checklist, and then you can get up to, gosh, I think it was 70 something pounds, and then you really have to go into the extra special duty stuff, in which case you've got a lot of extra checks and balances.
Well, 55 pounds is pretty good size. Wow.
Yeah, 55 pounds is pretty chunky. But I mean, I've met a number of a guy made a quarter scale or third scale GB, and he made it out of all balsa, and he says, I'm going to go over the 55, but not by much, I was like, holy cow, what do you, and it was fully skinned with balsa sheeting and all that stuff. And so it was big. So, I mean, I don't doubt it, but I was kind of surprised because I would imagine he would have tried to make it lighter so he wouldn't have to deal with all that.
Wow, yeah.
I guess at that size, the landing gear starts getting pretty heavy and the motor starts getting pretty sizable, and the fuel isn't just, a pound here, or a pound there, right? It's like, oh no, that's actually some serious weight, right?
Yeah.
So yeah, it's interesting. And then of course our ceiling limit is 400 pounds or 400 feet. And within a certain, and within visual range, right? Without doing other special stuff, right? Like we're working on those regulations now, and
so maybe you could actually help me with something that maybe it used to be that the regulations is you couldn't use the first person video from an airplane. You had to keep your eyes on it all the time. Has that changed?
You can use FPV, but you have to have a spotter who can see it unaided.
Okay.
So
Gotcha.
so they need to be able to see it. Obviously, they can have correction lenses, but they can't be like looking through binoculars. You're like, I see it still. Like, no, you have to be able to see it physically.
Very good. Okay.
So all I got to say is if you're going way out there, we won't get into it. There's a lot more to it, but that's the general.
Gotcha.
We're going to leave it there.
Very good.
So why don't we get into? I mean, did you have anything to add about the history? Is there anything you know about the history of ultralights that I missed? I mean, this was just a quick thing. It was from the National Air and Space Museum. I had a quick blurb about it. And I've actually seen both of these aircraft kind of hanging up there.
I think maybe the only thing to add is, it was really hot during the 80s.
Yeah.
And then toward the late 80s, a lot of ultralight airplanes were out there making ultralights. And they just weren't selling enough of them because there were so many companies. And so a lot of the companies went bust.
Okay.
And then just gradually over time, there are fewer people getting into ultralights. It's kind of leveled off now and kind of holding steady.
Yeah. And you remember we were talking earlier, like it's really tough to tell how many because they're unregistered, right? So nobody has to tell you if you got one or not, or if you're flying one or not.
Yes.
So nobody really knows how many ultralights. So the argument is there's about 20% of the aircraft in the air are ultralights.
There's something that's good and bad about that. There's the good part about not having a regulation is I can design an ultralight however I want to, and build it and
Right.
fly it in as long as I fly it legally. The bad thing is I can't learn from the mistakes that other people have made through like NTSB statistics and things like
Right.
that. And
Yeah.
so you
Because they're not
can't look.
reported and they're
Yeah,
not tracked.
there's no investigations that happen unless like the local
Yeah.
police department want to do it.
Right.
So
Or unless somebody has their own build log, that's assuming they survive. And
yeah,
they then document what happened so that everybody
yeah,
else can see it. Or
exactly.
they go onto the ultralight builders forums or something like that, because there's a couple places in the builder forums that you can go and
Yeah.
talk about ultralight stuff. So there's some spots, I imagine.
Yes,
But
there are
yeah,
some.
they're tough to find, I imagine. So
Yeah.
I never even thought about that.
So there's trade-offs to whether it's good to be regulated or not regulated.
I didn't think about it from that.
Yeah.
Yeah, me neither. That's good to bring up. Well, why don't we get into letting our listeners get to know who you are? Well, you and I have talked, so I've known you through your videos for a little while now, and I've gotten to know you personally as we've talked here and there along the way. But let's talk. Okay, so we're RC, right? We want to get the noobs in the air and get them through the hurdles as best we can. Or if you're here and you're older, in the sense that you've been in this hobby longer than a year or whatever it is, like you, hopefully our antics are enough to keep you entertained, maybe. But so did you ever get a chance to fly in the RC when you were little? Like, how did you start your love for aviation? Because obviously you have a passion for it.
Yeah. Well, my dad's been a pilot since he was a teenager, and he's always, when I was young, always telling us stories about him flying around, and he was also into RC. He had some RC planes. In fact, one of the first things I remember about RC planes is he had a single channel RC plane that he flew, and
How does that work?
So control line?
no, single
No.
channel.
So Leah, let's hear this.
One channel for both the rudder and the elevator. What happened is there was a hook that would come out the back end of the airplane, and it would rotate around, and there would be a slot in the rudder and a slot in the elevator, and as that hook moved around, it would move the elevator and rudder around. So if you were all the way to the left, then the rudder would be to the left, but the elevator would be in the middle.
Okay.
So, then if you rotated up, rudder's in the middle, but the elevator's all the way up. And I don't know how in the world they flew those back then, but they did.
So is that like a clockwork mechanism? It just kept rotating and you basically engaged or disengaged it?
I don't remember now. It seems to me like it was a left and right toggle, or not toggle switch, but a left and right switch like you would have on ailerons. And so moving it to left would make it go, clockwise, and to
Clockwise
right,
or
kind of,
anti-clockwise.
something like that. I think that's what it did. I don't remember now, but I was amazed that anyone could fly it at all the way they did that. That was
Yeah,
something
no
else.
kidding.
That took
takes
some skill.
Yeah, I mean, well, that's the other thing is you've got to build the plane really well to begin with, right?
Oh yeah.
If you're going to have any time with it, right, you're going to have to build it
Yeah.
well. And then you're like, oh, but the cool part is rather than just tossing it and watching it go really far, I can now put a motor on it and actually watch it fly for a little bit longer and enjoy every minute of that, right? And then go do it again.
Yeah.
You had some crazy stuff. The escapement, I think, is what they called it. Yes, I'm with you. I don't know how the heck they managed it. Okay. So did you ever fly any RC?
When I was about 8, I built my first RC. Well, it wasn't RC, my first model airplane, which was U-control with an 049 motor.
Okay.
Yeah.
Good old
flew
Cox
that.
049.
Yeah. So that was a lot of fun. Did that for a couple years. So until I was about 10. And then my dad and a friend of his bought a Piper Tripacer.
Oh.
And so flew around in that a lot. We there was 4 people in my family, and 4 people in Dad's friend's family, and so we took turns flying the airplane. So we flew out to LA and down to Padre Island and up to Chicago and all over the place.
Oh wow. Yeah.
So that went for quite a few years till about my mid-teens, something like that. Yeah.
Okay. Nice. So yeah, you were in full scale pretty quickly.
And then I kind of got out of aviation until I was had been out to LA for a couple years working there for TRW, and I got back into RC then. I was really interested in sailplanes at that point, and Loyola Marymount, which is up north a little bit, has this awesome hill where there's an onshore breeze almost all the time, and it's perfect for a sailplane. You just go back and forth along this hill and fly, and it's
Mm-hmm.
fantastic. So I had two sailplanes I built and flew there, and then I got more interest in aviation, so I actually went to the Torrance Airport and started taking pilot lessons, flying lessons. So I did that for a little while until I decided I needed to leave LA because they were burning down the neighborhoods at the time.
Oh
What?
boy.
Yeah, that was during the Rodney King riots.
Yeah.
Oh,
Yeah.
okay.
Yeah, I was working in a facility where they have pretty good security. And there was some burning going on a couple blocks away, so they sent us home early because if they were going to have to deal with rioters there, they didn't want us around.
Looking up pictures of that.
Yeah, it was kind of scary at the time. So anyway, I moved
Yeah. No.
back home, which is eastern Kansas, and decided I wanted to build ultralights for a living. So I started doing that for a year until so that was actually a pretty fun project. It was a steel tube fabric for the fuselage, and then foam and fiberglass for the wing or all the flying surfaces. And
Okay. What, like a wet layup kind of?
yeah, it was. Yeah. Wet
Okay.
layup. I didn't do any vacuum bagging or anything. I knew about vacuum bagging. I did not no, I'll take that back. I knew about vacuum bagging. I did not know about vacuum infusion at the time,
Okay.
which I really like.
I mean, so
Um,
those are the basic three, we'll call it composite methods, right?
yeah, pretty much, yes.
I
Yeah.
mean, there's a couple other variations on that, but
Yeah.
yeah. So the wet layup is basically you put right, you put epoxy down, you put the composite material, the fiberglass or the carbon fiber over top of it, and kind of either let it seep through or whatever, and then put another layer of epoxy
Mhm.
in and do that ad nauseum until you've
Right.
got the thickness you desire and you've
Yes.
double checked it for air bubbles and all that kind of fun.
Yeah.
The other methods are vacuum bagging, which is basically you kind of do that, right? And then put a bag around it
Yeah.
and then
Yeah. So
vacuum it. So
you do the
it,
wet layup and then put a bag over it and pull a vacuum so it puts pressure on it and
right,
squeeze excess resin out. Yeah.
right. And then and then also creates a really nice, smooth, as long as you've done it right.
As long as you've done it right,
it,
it's smooth. Yeah.
it creates a nice, shiny, smooth surface if the plastic's not wrinkled and all that kind of stuff.
Yeah.
And like you said, it gets rid of excess epoxy, which
Yeah.
keeps it as light as you can. And then the infusion basically doesn't let any excess get in there, pretty much.
Correct. Yeah.
And it sort of
Yeah.
pulls it from
You
one
you
end
use a
through,
vacuum to pull the epoxy through into the bag. Yeah.
and then in through the
And then
fiber
through the fat and then the fibers. Yep, exactly.
fabrics or whatever it is.
Yeah.
Okay, interesting. I just
Use
because again, a lot of our listeners probably, many of us haven't even looked at epoxy, and I have, but
Mhm.
there's if you haven't looked at it, you wouldn't know the difference between the different styles. So, but it's gonna it's kind of important. So you did a wet layup.
Yeah. Well, yes, it was a wet layup. That's correct. So that was going to be heavy, but I made the horizontal tail. I thought, this is working all right. I like it. Then I made the wing, and
Mm-hmm.
the way I did the skins, it was just foam with fiberglass on one side because I'd done the calculations that said, oh man, if I use fiberglass, I can't do a sandwich for the skins. So
Okay.
I decided, okay, let's try foam and then fiberglass just on the outside. And I got done with one of the wing panels and just handling it, moving it around, your fingers would punch through the fiberglass. And I said, okay,
Oh wow.
this isn't going to work. And
What
that,
what weight fiberglass was it? Because I know the
oh
rattan
gosh, it's
likes
so
9 ounces
long
per yard. I think is the
ago.
standard
I don't
rattan.
recall now. Yeah, I'd have to go back and look at my notes again.
Okay. Well, I
But
know in RC we use like half an ounce per yard, right? Like it's
right,
like crazy lightweight. We use maybe
yeah,
1.2 or 1.6 if we're trying to get a couple layers of
yeah.
heavy stuff.
So that's
Um,
almost a veil weight. Yeah.
yeah, right. So that's where you're probably getting the very lightest where you might even look at. And then of course, again, I looked at possibly putting together like a dragonfly or what would it take to build one at home, and the
Mhm.
rattan method when you look through their
Yeah.
whole thing, it's
Right.
basically they use 9 ounce per yard fiberglass.
Yeah.
So
Big stuff. Several
yeah, big
layers.
stuff.
Yeah.
Yeah,
Yeah.
it's like 6 or 7 layers at least. It's heavy, but I mean, I guess they're like, look, if you do this, you'll be okay.
Yeah.
You know, not maybe weight, but strength wise.
Yeah. So
So,
about that time that I decided this wing design wasn't going to work, I got a call from people I used to work with, and they said, "Come work for us." So I ended up leaving the ultralight building behind because I was going to have to redesign or something. I hadn't figured out what to do at that time.
hmm
So I got away from ultralights for several years, and then about the time I retired, I said, I want to build an ultralight again. So I started documenting it on YouTube.
nice. Okay, so that's how you got the decided to go. So, one of the things that that drew me to your channel was that you're not just documenting your process, right? You're documenting what it takes to design one because there's very little information on specifically building for ultralights. There's a lot of books about designing your own airplane,
Yes.
as you've kind of noted, right?
Yes.
In your other thing, and there's a lot of different methods that are proven, right? Like there's a lot of ultralights out there that have success.
Hmm.
Um, but if you want to create your own, where do you start? And how do you get there, right? Which is really cool. What I like about your channel.
Yeah.
So why did
Well,
you settle on that direction as opposed to just, I'll call it, making another build log?
um,
I
well,
mean, it would have been simpler, right, to just build a thing and be
well,
done.
sure, yeah. Um, One of the things that bothered me is when I decided I wanted to do a design in ultralight again, I went to YouTube and started looking for people who was talking about designing ultralights. I mean, there were plenty of people who were restoring or airplanes that were being built.
hmm
There's almost nothing on aero design either, and just in general.
Right,
So that kind
right.
of annoyed the heck out of me. I thought,
There's a
there's
couple MIT classes that go through some of the piloting aspects of it,
yes, a little
but they
bit,
don't. And there's, I think, one or two advanced courses in like, hey, you already know how to design stuff. Here's the details, and you're like,
yeah,
okay.
yeah,
But there's a gap in
there,
between of
yes,
like, here's a formula for lift, and then how do you get CL? And of course, the thing we talked about in our aerodynamics episode, which I think we're gonna continue to talk about
yeah,
here. But most importantly, just like how do you get, there's that gap. There was a gap. I mean, I felt like everywhere. I didn't look everywhere, but
yeah,
I looked in the NASA website, looked at their presentations and kind of like Greek. Okay, there's a formula,
yeah,
blah blah blah, and it works. It's like no. Go back. There's a step in there. There's like three things going on in here. They're like, well, you just pull up the chart and you do the thing and you get the numbers and there it is. Like, no. Go back. How did you get from this thing here to
yeah,
that next step where
yeah,
you're pulling a number into the thing? How did you get that number? Where did you pull it from? And
yeah.
that's what I love about your videos because you go through that step in a couple of your videos in enough detail where it makes sense. Where all that actually, that's the magic. To me, that's the part that goes, oh, that's what all these are for.
Yeah.
That's what all the charts are for. That's where the CL comes from. And this is why you're looking at these different parts of the chart and why these little bits of the curve are so important. So I
Yeah.
kudos
Yeah.
to you, by the way. Thank you so very much for making that
Well,
finally
thank you.
clear
Yeah, sure.
for the
I'm
first
glad
time.
actually it's somewhat working at least.
I think so.
Yeah.
Well, I'm gonna test it out here and see if it.
Although I did get a comment on one video, back in I think it was November. The guy said, "Blah blah 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 crap."
Wow.
I got a
Well,
kick out of that one.
yeah, that's funny. Well, and so that's the thing. It's like part of your channel is not like, hey, here's how. Just it's informational so that you understand what it takes to get there. And throughout all of your YouTube channels, you're like, look, I've got this thing, and I could make these spreadsheets I'm putting together available, but I don't want to because you need to come up with these numbers. Whatever
Yeah.
you're doing, you need to do. I'm showing you how to get there. I'm
Yeah.
showing you my example, but you need to come up with this because ultimately your life's on the line, right?
Yeah, absolutely.
Yeah.
Yeah, there's a lot of spreadsheets I've made that I'm not 100% confident that everything's correct on them, and I would hate just for someone else to go and use them and run into problems. Now, some of them
Yeah.
I'm positive are great, and I don't mind sharing those, and I've shared those
Yeah.
before. But some of them, like I'm working on now, is actually it's going to go along with the book I think I'm going to write. It could have all kinds of errors in it. I'm double checking it because I'm using it as kind of a backup design for the Unibus 4, and so far all the numbers are working out, so they're at least close.
Okay, good. You know what I found was interesting when you went over your CG video, right? Because CG is critical for every aircraft.
Oh yeah, absolutely.
The methodology that you use is identical to what we use in RC.
Sure. Oh yeah.
I mean, straight out identical.
Yeah, everyone's
like,
got to do the same thing. Yeah. Your data may be in a different spot. You still got to do the same process, though.
Yeah, same I was like, oh, look at that. And I mean, there's different ways of like now that it's like you can't just pick up the airplane and balance it on your fingertips, right? So like you got to do a little bit more math. Go a little bit more in detail, but it's really interesting. So yeah, if you, I don't know. So what would you say is your stated goal for the channel?
I would like to inspire other people to think about design, maybe design their own airplane. That's what I would like to see happen. It's something that's falling away. There's an interesting thing I learned at AirVenture this year, and that's the guy who works for Hummel Aviation. He's the CEO there. And he says that back in when Maury was doing his airplane design, which was in about 1990 or so, when he did the Ultra Cruiser.
Okay.
Lots of people were doing scratch build, and some people were doing kit builds. They would buy maybe the hard to make parts, and then they'd make a lot of their own parts.
Okay.
Nowadays, almost no one is scratch building.
Right.
A few are designing or building from kits, but most people want ready to fly.
Right.
And I think this is, I don't like it. I think we need people to do more building, and I would like to see people learning more design because I think we're losing those people.
Yeah. Yeah. Well, I mean, a lot of the people who are in it in those days, they're retired or they're ready to retire. And so that base of knowledge is leaving the workforce, as it were. And, you know, unless you're an RC enthusiast and going, how can I do more? That might be one avenue, right? Is to learn. Now, a question for you, because your aviation knowledge is extensive, as far as I can tell. Maybe it's not.
I always
so the
think
question
it's
is,
small.
I know you're probably I know
I don't know.
you're an electrical engineer by education, right?
Electrical by education, software by vocation.
Software by vocation?
Almost my whole career was writing software.
Okay, but you were aiming for.
I can tell you if you want.
you knocked on Joe's door right there. So I guess my question is you have a lot of basis of aviation on your channel. One of the things about me is like you started off wanting aviation, but in the 80s there was just a mass exodus from the whole field.
Yeah,
like everybody's getting laid off, and there was just like, oh, that's not a viable career at the moment.
Okay. Yeah, wait, that's actually worth talking about.
So
So,
obviously you have a love of aviation. It's been instilled in you since
I almost became an aerospace engineer.
Right.
So I'll tell you that story. So I was working at a small town, Lacine, Kansas, when I was a kid. Well, I guess I was a senior in high school, still a kid. And I was listening to the radio. We always had the radio on while I was fixing tires. And during that summer, which is the summer of 81, there was a whole bunch of layoffs going on in aerospace. And I had already told KU, which is where I was going to go, because KU has a fantastic aero program. At least at the time, one of the best in the nation. And so I said, okay, I'm going to go there and become an aerospace
KU
engineer.
is Kansas
University of Kansas.
University. Okay, go ahead.
Yeah, not K-State, different thing.
Okay. Yeah. Look, if you say NC State versus, oh God, I'm going to say it wrong, and then I'm going to get everybody pissed. Anyway, I get it. North Carolina has the same.
North Carolina versus NC State. Yeah. Anyway, I don't want to keep from getting off track. So there, KU had an orientation where you were supposed to go up there and fill out a form with these codes for what you wanted to be a major. Of course, you didn't have to declare a major, but so you could do the one you really wanted, then you can do a backup, which I don't know why they wanted that. But I was sitting there looking at that going, oh man, all these places are laying off aerospace engineers. I don't want to have to spend 4 years here and then not be able to get a job. So So I switched the orientation from aerospace first and then electrical engineering to electrical engineering first and then aerospace. And so I got a graduate and a master's in in electrical engineering at KU. Now,
Okay.
when I was a junior, I wanted to get some money to help pay for college. And there was an advertisement there at the School of Engineering for a place over on West Campus, which is the research center area. And they
Okay.
wanted someone who could do graphics design and not your normal graphics design, but someone who could write graphic software. And so, well,
Gotcha.
I had a Commodore 64, which I was writing a little game for. So I'd done some,
That's going back in the day.
yeah. So I'd done some writing for that. So I thought, what the heck? Let's see if they'll take me. So I went over and interviewed, and I started working there the next day. And that program was kind of boring. But while I was working there, another project came along, which TRW, which is based out in LA, they had aerospace division, and they wanted KU to write a software program for them to do communication system simulations. And so I got hired for that program too, same place, and started working for that, and got to know the guys from TRW who would come in and do assessments, see how we're doing. And
Mm-hmm.
my senior year, they said, "Hey, we'll pay for your master's degree if you keep working on this program, and then you can come out and work for us."
Hmm.
I said, "Okay."
Uncle.
So
Yeah.
that's how I became a software engineer.
Okay.
It was just a job to help pay for my way through school, and I end up just keep on doing it.
Yeah.
Why not?
Yeah.
Isn't that kind of how life goes? So, hey, kids, if you're just getting started, if you do not have a set path, be aware this is how it goes. Where somebody says, "Hey, I got an opportunity," and you go, "Oh, sure, what the heck?" And sure enough, before you know it, this is what you do. You have, I think every one of us has that kind of tale. Like, well, I was going to do this. I was thinking about this, and so maybe an offer to go that way, and well, here I am.
Yeah.
you know, whatever it is, building nuclear power plants, or going up in space or whatever. I don't know. Most people going in space are a little bit more deliberate than that. But
Yeah. But you mentioned earlier, learning about aerodynamics. When I was living out there, toward the end of when I was living out there, I got interested in airplanes. I was taking flying lessons, I said earlier, and
Mhm.
I wanted to start building airplanes and building ultralights. So I actually started buying books and learning about it, and I really looked into making computational fluid dynamics program. But I decided that
Okay.
was a
Yeah.
little bit bigger thing that I wanted to take on by myself.
Okay.
But I really looked into it for a while. So that's when I really started learning the nuts and bolts of design, learning all the terminology and lift equation and things like that.
Navier-Stokes stuff, or
Yeah. Well,
yeah.
generally don't have to really deal with that. Although when you get to the CFD, it's good to know some of
Well,
the
that's what I was thinking. Yeah,
ideas
because
behind it. Yeah.
yeah, interesting.
Yeah.
Really.
Navier-Stokes is our $1 million word right now.
Okay. That's good.
I mean, what do you want? It's the I'm not quite sure what that exactly is. I know that it is the key to fluid dynamic for analysis, right?
Yeah.
So,
Yeah.
for the CFD stuff. So, where is it gonna? I had a question for you. Well, ultimately, I guess, I mean, that kind of tells me and tells our listeners kind of know where you came from. Obviously, you've had a career kind of steeped in aviation. I know what it was. In the 80s, were there not a bunch of design books that kind of went with the craze of design and build your own aviation, your own
Yes.
ultralight?
Here we go. So one of the ones I really liked is this one by Martin Holman.
Okay.
It's a modern aircraft design. This one, I thought there's holes, but I thought this one was one of the better ones. There's some
Okay.
other ones I don't really want to say bad things about them, but I didn't like them.
Yeah.
That's probably one of the better ones. Oh,
I know your book, the book that Dan Raymer wrote is the
okay.
one you go to a lot in your
And
videos.
there's GA airfoils by Ribbler.
Yeah.
That's kind of nice. I learned a lot about airfoils from that one. I also learned some other things I didn't like, but anyway. And then there's a book by Evans called the Airplane Designer's Handbook, I think,
Okay.
which it has lots and lots of equations, but it doesn't have any description. So You kind of
Oh,
already have to know
interesting.
the equation, so
Okay.
But it
So
has a lot
it's
of
there
good.
for reference more
Yeah,
than
it's actually a great reference for things like, how much, column buckling you can handle on, like, round tubing and square tubing and aluminum, and it
oh,
has some
okay.
really good material properties in it that I think are a great
Oh,
reference.
yeah, because I mean that's the material that you use to build most of the framing, and most of it's either in tension or compression.
Yeah,
Period.
yeah,
And
compression is really the driving
big
thing, and compression,
right.
trying to calculate that sometimes is quite a challenge.
Oh, it's great. Come on, it's easy. Just kidding.
I did
I'm
do a
kidding.
video on column buckling, though.
Yes, yeah, it's good. Again, I appreciate the topics you tackle, and that I know that they're not all simple. Like they're not all like, oh, this is
Yeah,
easy. Like no,
yeah,
but you go through because you've had to learn it to get to what you're doing. You're like, well, let me show you what you need to consider because
yeah.
this is going to be important. And then, of course, you follow it up, at least in some of your earlier videos on the UWS one. You build your mock up and you say, okay, we're going to roll this because this has got to withstand a roll. That's the whole point of this thing here. So
Oh,
let's do
yeah,
it.
that's right,
You
the
know, and
cabin
then you
rolls,
like,
yeah.
first you check out, see does it physically fit?
Mhm.
Is it, are the things comfortable?
Yep.
Because if it's not comfortable, why am I building this thing?
Mhm.
and then, and that's got to be structurally sound. So let's mock this up. Let's without spending a ton of money on materials.
Right.
Let's test it because we got to test it without having the full plane here. It's just I really appreciate the steps you show that you. It's not just this simple. It should be good. Like no, it's
I occasionally
it's
do
like
that.
no. You may start off with a this looks about right, and you're like okay, well let's roll through the numbers. The numbers check out. Let's build a test. Let's test it.
Yeah,
The test worked like I thought, or no, it didn't and let's learn. Oh, see, it buckled here, which
right.
means it failed. And these spots that I knew they would be the weak points, but I didn't expect them to be as weak as they are. So
Mhm.
let's consider, and then you go back and kind of reassess and then
Yeah.
reevaluate, which is perfect. I mean, to me, what a dream! What a dream resource. So I really cool because it's in some ways we do it here, but we do it quickly or don't care,
Mhm.
because he's like I crashed. Oh well, let's do another one.
Yeah. Well, I
Um,
I think there's actually a even for bigger airplanes, I won't say full size, but for, like, ultralights, I think there's a place sometimes for just saying, "You know what? Let's just build this and see what happens," but
right.
doing it by testing it safely, not with you flying it,
Yeah.
but
See what happens with the test. Right.
yes.
Yeah.
Do a weight test, in the
Yeah.
lab, in the shop where you can actually see how it fails and learn from it and make it better.
Right. Right. Yeah. Well, because like you were saying, it's like, well, I want to try this and this. Well, I can try 3 or 4 different nose ribs,
Yeah.
or whatever, and then test them. And
Yep.
then I know which one's the one I want to use. And I go, okay, cool. This is the one I'm going to do. Let's get this all the way out and then build 20 or 50 of them or whatever you
Mhm.
got to build.
Yeah.
Well, cool. All right. So let's get into. You've prepared a small presentation for us
Yeah.
to go through some of the differences between full size aerodynamics that we've talked about in our previous two episodes ago or so. I think episode 87 or 88. Um, and then how that translates. Can you use some of that in scale aerodynamic? How do you scale it down? What do you got to consider?
Yeah.
And that kind of thing. Did I get that right?
Yeah. Well, what prompted it was when you and I were talking earlier, you asked me, did I think about building a scale model to see how it would perform?
Right.
And my answer was that not for this ultralight airplane. Um,
Okay.
and there was a couple of reasons for it, but I figured I could design this particular, since it's a standard configuration, big wing up front, small tail back in the back,
Right.
one engine, there,
Yeah.
if you follow the general design rules, you'll almost certainly make a safe airplane, at least aerodynamically safe.
Yeah.
Structural stuff's another issue. Um, so I figured that I probably really didn't need to make a scale model. Now, if I was doing something unusual, let's say a diamond wing or something like that,
Right.
then because there really are no good rules for that, then I probably would have made a scale model. But
Mm-hmm.
there's issues you need to think about when you're making a scale model, because if you're not careful, your scale model will behave differently than a full size will. And then so you're not learning anything.
Right. It's not helping you understand your full scale build.
Exactly.
Right.
So that's what I made a little presentation here, and we'll go through and talk about some of the issues between full size and scale models.
Okay, good. Joe, were you
Yep,
ready
it's
to?
already pulled up and we're ready to go.
Fantastic.
All right. So
All right, let's go.
Let's go to what our plan is here. So there's 3 areas that we'll talk about. One is airfoils, and this will kind of carry on from the podcast that you guys had on aerodynamic lift. And so I'm going to review something that you guys talked about, which was the lift curve, and talk about the differences between full size and scale size. And there are some differences there.
Okay.
And then we'll talk about how do you go from airfoil information to designing a wing. And then we'll go to kind of a scale on a larger scale, like the whole airplane. If you scale it down, what happens? Or is there a way that you can select scale, weight, and speed to get similar performance to a full size airplane?
Okay.
All right. So let's go to Reynolds number. I think you guys mentioned this before, right? You went over Reynolds number a little bit.
We did. We did the best we could.
Yeah. I think you guys did. By the way, I wanted to mention you guys actually did a really good job. That's a tough topic to tackle. And I think you did a great job on your podcast.
Well, thank you so much for that.
You bet.
Yeah, big thanks. It's one of those ones we were like, I don't know. And the deeper we got into it, we're like, ooh, this is a lot.
It's a rabbit hole, yeah. Or at
But
least
at the
it
same
can
point,
be.
I feel like it's important, for those who want to go further than just I build a plane, I fly a plane, right? Who want to maybe tackle design, I appreciate that. Thank you so much.
Sure.
Go ahead.
So let's talk about Reynolds number here. Now, it's trying to wrap your head around what a Reynolds number is kind of tough, but using it actually is pretty easy. And we generally use Reynolds number when you're comparing things. So you might be comparing airfoils, and so you might look at the different Reynolds numbers you might use it at and see how airfoils behave differently, their lift curve and their drag and such. And so that's kind of what I'm saying here. And there's Wikipedia basically says that you're trying to compare maybe a full size or a model version, and you're doing that for different fluid dynamic situations. So let me go ahead and go to the next slide. Yeah, okay. So a lot of times when you're comparing airfoils, you want to compare them at the same Reynolds numbers to see if one is better than another. You want to compare apples to apples.
Right.
I probably should put a different order here on the slides because I talk about the equation next, but let's go ahead and do it in this order.
Go ahead.
Okay.
Hey, I want to interrupt real quick.
Oh, yeah. Always interrupt if there's a question.
For the benefit of those who may have forgotten, not pointing fingers at myself here, can you give a brief, and you may have quickly mentioned it, but can you give a brief explanation of Reynolds numbers and what it is?
It's hard. Let me go down here. So here's the equation. That's probably the easiest thing to talk about.
Okay.
So a Reynolds number is basically an aerodynamic condition for something going through the air. And the Reynolds number is calculated using a speed and a length. And that's almost all there is to it. There's a kinetic viscosity or kinematic viscosity, which is basically the absolute viscosity divided by density of the air. But I kind of ignore that. I just use whatever sea level is and just always use the same number. So once you get that number, you can ignore the rest of it. So what your Reynolds number then is a combination of speed and length. And if your Reynolds number is the same between airfoils, you at least know that you're comparing apples to apples. So the combination of speed and length, as long as it's the same, and this is what's really bizarre. Let's say you go twice the length on an air chord of a wing. If you go half the speed, you're going to have the same Reynolds number. Something else, does the opposite.
Right, so if you do a quarter scale, you got to go 4 times as fast.
Exactly, which is actually right down. Where did I? Right down here. So that's example.
Out of order. I'm sorry.
That's okay. That's the example down here. So what you just said, if you're going a quarter the chord length, then you have to go 4 times as fast to have the same Reynolds number. So you're comparing apples to apples. In fact, the airfoil behave the same. So if you have, let's
At that
say,
speed.
yes, that speed and
Okay.
length. So that's what's really nice is you can actually compare apples to apples. Now, something we'll talk about a little bit later is going 4 times as fast for a quarter scale probably isn't practical.
Yeah,
Oh,
that's
not at all.
moving. That is moving.
Yeah.
Well, can you change the? No, I suppose not. I was
So
thinking
so if you
the
want to use
cross-sectional area or whatever.
so this is kind of what we're going to get to on if you want to go quarter scale or any kind of scale, if you want to use the same exact airfoil that gets similar performance, you're going to have to go a lot faster.
Right.
There's just no getting around that part. Which is why, sometimes people will build scale models that have the same airfoil as a full scale, and the darn thing won't fly. It doesn't have enough lift. It stalls low speeds. You're going, what's the deal? It's not behaving the same. Well, you'd
Right.
have to fly it faster to get the same behavior.
So a nice way that, and I know I reference them a lot. I like them. Ron and Tom do the aviation. They do the RC Plane Lab podcast. And a long time ago, they were talking about Reynolds numbers and such.
Yeah.
And the analogy or the statement that Tom had made was, you can scale down the size of the wing, but your molecules of air are the same size.
It's still
Yes.
as sticky no matter what the
It's-
size.
Yeah, you're scaling things down, but you down.
Yeah,
essentially.
exactly. Yeah. So in order to get the air going over it the same way as full size, you got to fly a lot faster.
Mhm.
So that's basically what Reynolds number is used for, is comparing airfoils, either the same airfoil at different scales or different speeds or length. In fact, let's go back up. Okay, so I have this little something here. So you can, like I said, you can compare different airfoils at the same Reynolds number. If you're comparing airfoil to airfoil, you probably want to have the same Reynolds number. And I didn't put it here, but you probably also want to have the same thickness, because
Okay.
different airfoils will behave differently at different thicknesses. And when I say thickness, I'm talking about thickness ratio. So where the maximum thickness of the airfoil is compared to the chord. So that's a thickness ratio.
If you were to scale the airfoil down, you're still keeping the same ratios.
You would keep the same ratio, yeah. If
Alright,
you
go
want it to
ahead.
be a scale, exactly.
Yeah.
Because I see some guys, when they're comparing airfoils, they'll compare like a 14% to a 16%. And you're not comparing apples to apples when you're doing that, even at the same Reynolds numbers, because airfoils behave differently at different different thicknesses, which is interesting. I still have a hard time figuring out, when I change the thickness, how it's going to change the behavior of the airfoil. It's
Mhm.
there's a little bit of black magic there that I still don't have a good handle on. Another thing
Okay.
is, so you also want to maybe compare the same airfoil at different Reynolds numbers, which was what we were just talking about. So different speeds, how is it going to
Okay.
behave at cruise versus stall? Because at stall speed, which is a lower Reynolds number, it could behave way differently than at cruise.
Mhm.
Also, you'll get different Reynolds numbers if you have a tapered wing. The root will have a larger Reynolds number than the tip. So you'll want to do a little investigation of that, make sure that tip's going to work okay. And then, like we've been talking about, full scale versus model.
Mhm.
And calculating your Reynolds numbers, I love using spreadsheets for that. So I've got a little spreadsheet that has like that kinetic viscosity, and I have conversions for knots to feet per second and Mach to feet per second and meters to feet. And then I just have different sections here. Like this is the one I use most often, which I have the wing chord, and I have
Mhm.
speed and knots, and then it'll compute the Reynolds number for me.
Okay.
So, and then occasionally I'll be reading on a book where they talk about some Mach, runs a little bit of certain Mach. So I've got one for doing Mach speeds. Right there's one.
Oh, okay. Yeah.
So, yeah. So I
So
love using the.
why is it more just so that you can compare mentally apples to apples?
Yes.
Okay.
Yeah.
I mean,
Exactly.
otherwise it's fully translatable, right?
Yeah.
Feet per second versus knots versus.
Yeah.
Okay.
And I should mention, you have to be careful of your units. Your speed has to
Always.
match the length units and your kinetic viscosity units. So if you're using feet, use feet everywhere. If you're
Yep.
using inches, use inches everywhere.
Yep. Otherwise, the units don't cancel well.
Yeah, things don't. You get bizarre answers, which
Yeah.
occasionally I've forgotten
So
to do that.
if you're new to engineering, always write out your units and cancel them. And if they
hmm
don't cancel, you may have to convert something
Yeah,
or whatnot. So be very careful.
exactly.
Without
That is one of the things that gets beaten into us in the early days of training.
without getting too far off track, and maybe the story is wrong, but I remember growing up with a story that when they were doing the lunar landing the first time, that the lunar lander would have crashed if they had not taken control of the lander because the units were programmed in one system, in part of the system, and programmed in another unit in another system. Uh, Feet versus meters or something like that. That may have been wrong, but
There
that
was a Mars lander where that happened. Where
maybe it
they,
was a Mars lander.
yeah, yeah.
But I thought there was something with the lunar lander.
Well, the story I remember is that when Neil was coming down, it looked like their programmed landing point was going to be a boulder field, and so he decided to go extend the landing out a little bit farther to get away from the boulder field. But it
That may have been where that.
now they were having a program error on their computer, saying, "Hey, you got this error, like a what was it, 2201 error?" And they're saying, "What's this 2201 error?" And so some guy down at Mission Control had to go look up and figure out what it was.
Wow.
It turned out it wasn't a big deal, but yeah, that was kind of scary too.
Yeah, imagine.
Yeah.
No, Joe, I'd never heard that. So that's interesting. I'm
But there,
sure. I'm sure the tales of all the old, the way things used to get done. They all sorts of stuff like that. I mean, that's easy to do, right?
oh yeah, especially if you got contractors or using
Right.
you got a European agency that subcontracted to U.S. Subcontractor, and they're
You-
not using the same units. Absolutely.
Do you work for my company? I'm sorry. We currently work at effectively a worldwide company, and
hmm
uh, us and a couple other folks are like the only Yahoos that are using metric, but it's being built in America. So all the other
mm
folks are like, what units are we using again? Why are we doing this? Like,
Yeah, I'm
if you're an
thinking.
American contractor, you know why.
I'm thinking one of the future ultralights I'm going to do. I'm going to use metric units for the whole thing.
Okay.
Yeah.
I'm sure there's a whole population of folks who are going to be very happy.
Yeah. Yeah. That'll be good.
Yeah, well, go ahead. Yeah.
Okay. So we talked about trying to keep Reynolds number the same, but what if it's going to be different? How does that affect your airfoil behavior? So let's look into that.
Okay.
So this is a lift curve that's similar to what Matt showed during your previous podcast. So
Hmm.
this green line here is the lift curve. So over here on the left is your coefficient lift. On the bottom is your angle of attack. So as you increase the angle of attack, you increase your lift until you get up to the maximum lift. And after you go past that, you start stalling and you start losing lift. Now, this green one is one of my airfoils. It's the UAK-02 at a Reynolds number of 1 million. That's pretty close to what the stall speed is going to be for my ultralight airplane, a Reynolds number around 1 million. It's a little higher than that, but this is good enough. But let's say when we want to build a scale model of the UWS-4, and let's say we make it fly, let's make a quarter scale model, and let's make it fly at about half the speed, which would be about a hand launch speed, which is a little
Right.
bit tough to do for a quarter scale model, but let's just go with it. So that'd be a Reynolds number of about 125,000. So let's
Right.
look at what the same airfoil does as 125,000 Reynolds number. So now you can see it starts diverging, especially when you get up here to the maximum coefficient lift. And in fact, you can see how jagged it is. That's because XFLR5, which is the program I was using to generate this, is having a terrible time trying to converge to solutions at these higher angles of attack. And then
Okay.
you can see that it drops when it starts converging again. It's way down here. We lost a whole lot of lift
Really
Yeah.
quick.
very quickly.
Yeah, between 15 degrees and 18
Yeah,
degrees, it
so
drops one
about
full.
about 3 degrees, yeah. Now, this at these Reynolds numbers, another thing that you can get happening is a hysteresis, where that's what this red arrow is. In order to get back to this lift curve, you'd actually have to start reducing your angle of attack, but you're also losing lift until you
Mm-hmm.
get down to a certain point, and then as you're still reducing the angle of attack, your lift starts increasing until you join the line again. So that's really terrible.
So to recover, you have to make it way worse before.
Yeah,
making
you
it
have to
better.
make it way worse before you recover. So some airfoils will actually do that.
So he's basically saying keeping the same slope at the stalled slope, right? Bring it back to 12 degrees and 0.4 coefficient of lift. That's
Yeah.
like the worst. You
Yeah.
have to bring it all the way slope back to that, and then
Yeah.
pop. And then as you get lower angle of attack from 12 degrees, it goes up to 1, basically as you get to about 5 degrees angle. I'm
Yes.
saying this for the
Yes.
audio listeners, right?
Yes.
So so it kind of comes up, but yeah, so you're really in. If you were counting on coefficient of lift of 1 for most of your higher angle of attacks to recover from this, you're basically going to be stalled out and in a dive, or heading straight towards a dive.
I mean, this is hard to
without
recover
any.
from. This is horribly dangerous too. In a full-size airplane, you don't want this, because if you got
No,
some
you're
guy that's
going-
pulling back on the stick, he's
No.
never going to recover.
Never going to recover, because you're
And in
never going to
fact,
let it
pushing
get down to
in
that.
fact, pushing forward just a little bit won't even recover you. So
Yeah.
you got to push way forward.
Right.
More than 10
almost
degrees.
7,
Yeah.
7, 8 degrees.
I'm trying to figure out, and it's just the dummy in me, I guess. Why doesn't it just follow the graph backwards? Why does it have to have a?
It's a good question, Joe.
No, not all the airfoils do that. Some will, and partially is, you can see down here we completely lost attachment. The boundary layer is completely detached. In fact, it's detaching at the leading edge. It's not attached anywhere, and you got to get it reattached.
And the reason
Now-
why he knows that is because of how sharp the drop off is. Is that
Yes.
how you can
Yes.
tell?
Oh,
'Cause
yeah.
that gentle curve shows that it's detaching on the back half of the wing. That's
Yeah,
that
the
gentle
green
curve.
one, exactly.
Anywhere it's sharp
Yeah.
means the leading edge is where it's starting to
Yeah.
lose.
Yeah. So, like he was saying, on this green one, where the very gentle curve, very gentle fall off,
What's
the
the
way
Reynolds
it's
number of a million?
with the way it's detaching is from the tail, the back end, the trailing edge first, and it's slowly, as you
Slowly
increase
moving
angle
forward.
back, slowly moving forward. So you're just slowly moving the lift, and usually it'll reattach normally as you start lowering the nose and you start coming down in angle of attack. That's because of the shape of the airfoil and the Reynolds number. But down here, you've got a sudden loss at the leading edge. It's detached at the leading edge first, and usually that's because the sharpness of the airfoil. When you're scaling down, that roundness is getting smaller and smaller as you scale down, and it's getting sharper and sharper. And sharper leading edges will cause leading edge separation of that boundary layer, usually. Now, you can actually get around it, but for the most part. In fact, I got a slide later that'll talk about that.
So
Okay,
so
it
to
seems to be
restore the boundary layer, it has to recover almost completely
Almost
to
completely.
reattach that
Yeah.
boundary layer from the leading
Yeah.
edge back, and then from there it starts
Yeah.
regaining lift.
Like I
Right,
said,
'cause
these
it's not-
airfoils are magic.
right, because maybe in theory or whatever word I'm searching for is, I guess in practice, the sharp leading edge is not allowing the. Would that have anything to do with is it the Coanda effect? Where
Well,
it's not wanting to wrap
airfoil,
the skin?
airfoil has momentum. Remember your Navy or Stokes where you have momentum in there?
Mhm.
Your air particles have momentum, and you're on a sharp leading edge, you're asking them to make a huge, fast curve.
Right.
And it's hard to do that with a sharp curve. The more gentle it is, it's easier to stay attached. Doesn't have to, your momentum makes you, I can handle this pressure difference as I go along. But if you're asking to make like a 90-degree curve to go around a sharp edge, it's saying, oh man, I can't do that. I'm going up. Instead of going around, I'm going up.
Right. So once you have boundary layer separation, with this airfoil that we're referencing at these numbers, and again, a sharp leading edge because we've scaled it down.
Yes.
Even as we decrease the angle of attack, it's not overcoming that sharpness to stick again.
Yeah, it's not reattaching. Yeah, exactly.
Wow. Okay.
This particular example. It doesn't happen every time when you scale down. It's just
but it
something.
can, and when it does,
yeah.
It's nasty.
And so
Yeah, it's very
think
nasty.
about it this way, it's like when you're pouring that pitcher of water and it starts coming around the bottom. It's like it comes out and then it starts coming around the bend and then it separates again. But to get it to come back around, you got to really tip that pitcher back all the way up. I guess it's really a terrible way to think about it. But my point is you can't just restore it back to that spot where
Yeah.
it started to jump off. You have to go way past it to get it to restore that coend effect flow, and then you can kind of pitch it back over again. I
Now,
guess.
I should mention that it isn't true for all low Reynolds numbers, though. Once you get lower and lower, even a flat wing will actually start working, even though you got that sharp leading edge. Once
Hmm.
the air gets more viscous for the Reynolds number, that lower Reynolds number, it'll actually, because it's so sticky, it'll stay attached better.
Hmm.
So it's bizarre the way airfoils can change over Reynolds numbers. I mean, it can behave completely different. You can go, really low Reynolds number behaves one way. You go kind of middle 100,000s, it behaves another way. You get up above million, behaves another way. In fact, you go up to 10 million, it changes again. So,
Okay. Which is why
which
I
is
guess
why you
like
need to
Klein
design.
Fogelman.
Go ahead.
I was gonna say which is why Klein Fogelman wings work at low Reynolds numbers.
Mm,
They're designed to work for like basically paper airplanes and a little bit bigger.
yeah.
And then
So,
after that, it's like okay, yeah, just use an
yeah,
airfoil.
airfoils really should be designed for whatever Reynolds number they're going to fly at,
Yeah.
or
Interesting.
range of Reynolds numbers. Yeah.
Yeah.
Which is what the UAK 2 is. It's designed to be an ultralight airfoil.
Hmm.
So fly between about a million Reynolds number and 3 million. Okay, so we already
Exciting.
talked about this. So, oh no, I love this one. If you guys haven't ever read Horner's book or looked at Horner's book, um, this guy, he's got a massive book just on drag. He's got another book on lift, and I love these books. In fact, you can find them online in PDFs. So,
Hmm.
um, they're he took decades and decades of research and condensed it down into books. So all
Okay.
those NACA reports, he looked through all those and all the private airplane company reports that he could get to, and he condensed all that data down into books. And so it's a gold mine of information. I find all kinds of good stuff in there. In fact, recently I was working on trying to figure out the coefficient of moment for wings with flaps and without flaps deflected, and I found something in there that answered my question. So it was pretty cool. All right, so I like this. So this is out of Horner's book, and he's got 3 different kinds of airfoils here at different Reynolds numbers, 2 different Reynolds numbers. So he's got a flat one, like you might find on an airplane like this, the old balsa wood airplane, little glider, as just a perfectly flat wing. So that's this one here. And then he's got the same wing with a little bit of camber, so it's got some curvature in it. That's
Hmm.
this one up here. And then he's got a 2-surface airplane, like we've been talking about for the most part.
Clark
And
White.
so, yeah, something like Clark White, exactly. But it's down here, it's usually fairly thin, and we'll talk more about that here in a moment. So down here at 40,000 Reynolds number, the flat but curved one, or I should say thin but curved one, behaves reasonably well. This is coefficient lift out here on the left side. This is coefficient of drag on the bottom. Just kind of ignore that. We're really just looking at the coefficient lift. So as coefficient lift goes up, we can see that the maximum coefficient lift up here is pretty high for this curved one that's really thin. Come down on the perfectly flat one, it's not bad, but it's not great either. It'll work, which is why these little gliders work so well at such low coefficient, or sorry, Reynolds numbers. So
Mhm.
even these things can fly fairly well. Not great, but fairly well. But what's really surprising down here at 40,000, this 2-sided wing is the worst one. Its maximum coefficient lift is terrible.
Hmm.
But go up just a little bit by a factor of 3 on Reynolds number. So this curved one, the flat, thin
Which
curved one,
which
and
doesn't
the
really, by the way, which doesn't take a whole lot
oh
to
no,
go.
oh
I
yeah.
know everybody's like,
Well,
oh, that's like no, no, no.
well,
There's a
so
very
either
minimal
increase your
difference.
speed by 3 or
Yep.
increase your chord by 3, or multiply them together and increase by
Yep.
3. So that's the way you'd go up to 120,000.
Okay. Right. Anyway,
So
so I just wanted to point out that like
oh yeah.
those number differences in Reynolds numbers aren't as dramatic as they seem.
Hmm. So the flat one is the same, and this curved thin one is the same. But your worst one before at 40,000 is now the best one at 120,000. So, like I was saying, you can get huge performance differences between, not a great range of Reynolds numbers.
Mm.
So that's the only reason I brought this up, is just to show that you can get. And if you want to learn more about this, get Horner's book on fluid dynamic lift, which you can actually find PDFs of on, and it's page 2-17. So you can actually read more about that.
We'll provide a link in the description. It's in usarchives.org. You can look up.
Are you
online.
making a note of that, Matt?
Yep, already got it.
You already got it. Look at you.
I know. I'm on top of it sometimes.
So I guess I didn't mention what coefficient lift is, but you guys did that in your video, so I think that's probably good.
Okay.
All right. So Horner says something about, for any Reynolds number that's below about 100,000, what are some of the general characteristics you're going to see? So let's say you want to do a 2D airfoil. He says that you really need to reduce your thickness ratio. So maximum thickness over your chord length. So as you reduce that, you get better performance, which is what we just saw. The really thin ones actually behave fairly well. The 2D that had some thickness didn't. So he's saying if you're below 100,000, you keep reducing that thickness ratio until it starts performing better. And
Okay.
we just saw this on the previous slide. But
Yeah.
this is true for wings and your horizontal tail and your vertical tail, because they're generally actually a lower chord, so they're operating at a lower Reynolds number, which is why if you look at all these old airplanes like the old Pipers from the 50s that were tube and fabric, they're basically flat.
Yeah.
They don't have much airfoil shape to them at all, but they work pretty well. Now, part of that's just because they're a low aspect ratio, which we're not going to talk about today. But they're flying at a lower Reynolds number, so they behave better than a main wing that was flat.
Okay.
And so this talking about this, making things thin, is actually why your foam board works on these slow and small airplanes. Foam board works great because it's flat, and so it's thin and flat. So that's why it works so great instead of having like a perfect airfoil shape.
It actually really helps explain, if you're familiar with the old Foky, it's just an undercambered wing. Basically,
it's like
two lines, if you will, bit up and then down.
Yep.
And that thing has insane lift.
Yep, definitely. All right. See if we should talk about this. This is just talking about the UAK2 again. So it was designed specifically to operate up and around the best operation or best characteristics at 100 million, between 100 and 100, or sorry, I said that wrong, 1 million or 1.5. So that's what it was designed to operate at. So it's got a really thick airfoil, like 18%. And now part of that is just because I wanted to make the spar lighter. The higher or deeper your spar is, the lighter you can build it.
Right.
And so that's why it's so thick. But it's got a really high coefficient of lift, especially at the 1 million area. It's got low coefficient moment, which we're not talking about today, but if you know a little bit about it, that's what that's is designed to have low coefficient moment. That coefficient moment causes.
We talked about it. It basically allows you to keep a smaller tail.
Yes,
and
exactly.
reduces drag.
Yeah,
Yep.
because the coefficient of moment of the wing tries to make it pitch down, the nose pitch down. So the less pitch down you have, the smaller you can make your tail to counter that. So that's nice. And
which is why when you look at flying wings, they have almost no coefficient of moment.
Yes, exactly.
Flying wing airfoils. So
or they make it so the center section or the outer section counters the center section. So yeah.
Yep.
It's got a moderate drag. It's not great, but it's an ultralight, and we need drag to keep below the 55 knots that are required to meet. So I'm not too worried about drag.
We become speed demons, and the air police come on and say, "Hey, now." I saw you go so fast.
And then the other thing is a broad stall curve. In your scale, you're probably not too worried about that, but this airfoil was designed so it never has a steep stall. It has a very broad stall. It actually just keeps falling off very slowly as you come farther out in higher angle of attack. I didn't want to have a stall that would just suddenly break and boom,
Right.
your nose down. You could actually hold back the stick on this back in your chest, and it'll just come down with a high drag without the nose falling down.
Right. They call it
Kind
mushing.
yeah, mushing exactly. So I
Yeah.
wanted to have that. So it's
So
designed
his airfoil, if you're listening, it basically goes from a coefficient of like 0.3 or so at 0 angle of attack, and then at 20 degrees is just about where we'll call it officially stalling. That's
Yeah.
the maximum coefficient of lift, and like he says, out to like almost 30 degrees is where it kind of falls down to like 1.2 maybe. So it
Yeah.
just sort of mushes, and instead of being really high lift, it just is less. And
Now,
so if again, if you're coming in for a landing, you're just gonna kind of ease your way down.
yeah. Now, the other nice thing that's about this curve, especially if it's for the whole wing, generally in airplanes you're flying in, you want this root of the wing to stall first, and then as you increase angle of attack, that stall starts
Mhm.
spreading slowly out toward the tips. Well, the nice thing about this really broad curve is you don't have the root suddenly stall sharp with the outer tips still flying. You can have the outer tips over here at, let's say 15 degrees. That's
Mhm.
another thing to mention is the angle of attack along the wing isn't the same. It actually changes as you get out towards the tips. So the tips might be flying at 15, 16 degrees, and the root's actually flying at 22 degrees. But I've got
Yeah.
a lot of coefficient of lift over here at the root, even though it's stalled. So I have lots of lift even as I'm starting to stall. So I like
So
that. It's
so
good for an ultralight.
you're almost gonna be able to keep level flight. You just won't
Yeah,
go higher. And remember, if you remember the coefficient of lift formula, it's based on speed, coefficient of lift, right?
I've got
So
I got it
as you're
later.
slowing down, right? That's the whole. Okay, you got it over there.
I
Okay,
got it later. Let's go ahead and
yeah. Then go ahead. Then let's talk about that because the whole point of as you're coming into land, you have a high angle of attack to get as much coefficient of lift because you're reducing your velocity.
yeah.
Yeah.
So let's talk a little bit more. We'll use this airfoil as an example of what happens if you scale it. So let's talk about Reynolds numbers below 400,000. There's all airfoils have a kind of a critical Reynolds number that's probably about 500,000, where the
Mhm.
behavior below that changes a lot compared to above it.
Right.
So
We saw that when we looked at our list of airfoils and then the ranges
exactly,
of Reynolds numbers. At a certain point, like you said, around the 500, it just started to get weird,
so
like yours shows.
yeah, so Horner said go with a thinner airfoil. And he also
Hmm.
said, which I didn't mention it, is increase the camber too if you want to. So let's compare the normal UAK 02 at a million compared to, well, let's see, I went to quarter scale and half speed, 120 some thousand. So let's pick a thickness
Okay.
8% and a camber of 5.5. So that
So
increases. So we
okay,
had
so
a
you
camber of,
reduce the thickness by almost
yes,
half, by over half,
yeah,
and increase the camber by an extra
one and a half
30%.
percent, 1.5, yeah, exactly,
What
yeah.
it's yeah, 30%
Yes,
more
yes,
than it
yes,
was.
yes.
Right.
All right. So here's what it looks like visually. So the green one is the regular 18% thick airfoil. The blue one is an 8%, which you just talked about. And I also
Hmm.
did a yellow one, which has less camber
Almost like if you
because,
were to just shrunk the wing down, let's
yeah,
say
if you
thickness
want it
wise.
to look scale,
Yeah.
here's the problem. This blue one is the 8% one, and you can see it's got a whole lot of under camber here, and so it doesn't
It
look
does.
scale anymore.
This has
So
a
I said,
what looks like
well,
a sharp edge.
so what would happen if we had 8% thickness, but we only increased the camber so it's kind of flat on the bottom? So let's
Okay.
compare that.
Yeah.
So here we are. So here's the green one, still unchanged at 1 million. Here
Mhm.
is the red one, which is still the UAK 2 at 125. And then I also did at 125 for the 8% one that's still cambered. So you can see by even though I made it much thinner and increased the camber, it's almost got the same coefficient lift as the original one. So we've gone from this point here where the red line is at about 14 and a half up to a
Mhm.
little over 1.6. So we're almost up to the green one. And we could probably increase the camber more and go ahead and crank it up. But I like that it has not a great fall off on the stall, but not bad. Not nearly as bad as the
Right.
red one.
Right. It's not a steep drop off where
Yeah.
the whole wing loses lift quick. It does drop, but it's not
Yeah.
dramatic or as dramatic.
And
And
then
then
I
of course you
wanted
have
to,
the flatter wing.
yes. So here's the one that's still 8% thick, but I didn't put as much camber on it. That's this yellow one. So it's got a fairly nice drop off here on the stall, but the maximum coefficient lift is only about 12.5 now. So without that
Okay.
camber, the lift's going to fall on us.
Right.
So it's kind of comparison of what happens with various airfoil shapes, what you can do with more camber and flatness. So if you want to
Okay.
make it scale, look at scale anyway, make it thinner and probably reduce the camber, you're going to get less lift, but the stall characteristic will be closer than if you just, left it a sharp nose.
Right. It'd just be at a smaller or shallower angle of attack.
Yeah.
Okay. Interesting.
Yeah.
Hmm.
So
And
there's,
because we're looking at
losing
this. Now,
Joe.
No, I'm just taking it all in, and it's little adjustments, and
Yeah.
it's mind-boggling.
Huge difference in performance with just what seems like minor adjustments. Now, I guess I should mention the program I'm using here. I mentioned a little bit before is XFLR5. It's an easy to use program. You can go to what is it, Airfoil Tools website. You can download coordinates for airfoils and then load them into XFLR5 and play with them. You can do this yourself.
Yep.
It's easy to do. So
it's mostly what a 2D analysis.
Yes.
It
Well,
gives you curves based on the plot of the wing airfoil.
yeah, it can actually do a whole airplane, but the main part of it is just doing section coefficient lift. Yeah.
Right. And then what's the other one that you use for if you're designing a full?
I use OpenVSP for
OpenVSP.
configuration and a lot of air or wing analysis. Yeah.
Okay.
That's
one I was thinking of.
Yeah, I like it a little bit better.
Okay, good.
All right. Okay, so we talked about coefficient lift and how it changes, but how can we use our coefficient lift to make a wing? So here's where we're going to get into that equation you were just talking about, our lift equation.
Okay.
So the lift equation, probably the simplest form, is your lift, which is weight, is going to equal your surface area of your wing multiplied by your dynamic pressure multiplied by your coefficient lift. Now, you may have noticed that back here when I'm talking about coefficient lift, see me go back a little bit further. Uh-oh, how far back is it? Never mind. I'll just say it. So when you're talking about airfoil section coefficient lift, you use a small L. That's this little L here underneath the C.
Okay. It's
when
not
you're talking
about CI.
I know. I need to use a different font.
It's a lot of fonts that do that, man.
Curse you, Arial.
But if you're talking about the coefficient lift of a wing, you use a capital L. So if you see a small L, is section coefficient lift, just the airfoil, big L, the whole wing. So that's why I've got a big L over here on this wing coefficient lift. You should always have a big L here. Okay. But, how do you get from small L to big L? And we're going to talk about that. So I use this equation all the time. But there's four different unknowns here. Or it can be three different unknowns or, whatever. But usually there's going to be three things you know and one you don't. So I rearrange this equation all the time. I may have the lift I want and dynamic pressure and coefficient lift, and I need to say, well, how much surface area do I need? And so,
sir, I did not sign up to take an algebra class here.
Well, that's why I did all the math for you. Come on.
Yeah. Let's say you want to know what the coefficient lift of the wing has to be. So as long as you know the lift and dynamic pressure and surface area, you can calculate what you need to have for your coefficient lift. And that's usually the direction you go. You're trying to figure out how much lift you need.
Mm-hmm.
And then velocity. So let's talk about dynamic pressure. And it's kind of funny. Back when I was first learning about this stuff, you'd see rocket launches and they'd say, oh, we've reached max Q. Well, that Q is dynamic pressure. We use the same thing here. Okay. So to calculate your dynamic pressure, you take your air density, that's the Greek letter rho, times the velocity squared, and then multiply 1/2, and that gives you your dynamic pressure. So that's all it is. And I use this since I'm using imperial units. This is what you can use for air density, and that's using standard atmosphere at sea level.
And that's like slugs per cubic feet.
Yeah, slugs per cubic feet. Yeah, exactly. And again, you have to be really careful here with your velocity. Use feet. You don't want to use a mile per hour or something. You got to convert to feet per second.
Because you want your Q to be pounds per square feet.
Yeah, because your surface area is going to be in square feet, and your speeds, or sorry, your densities in cubic feet. So you need to have all your units match up.
Right, and your weights, you want
lift is going to be in
pounds.
Pounds, right?
Right. Yeah. So knowing that these are the things you're working with, you want to keep in the same units.
Yeah.
Don't goof it up. You'll regret it later.
So the other things is like calculating your stall speed. If you'll know your lift, so your gross weight, you know your density, you know your surface area and coefficient lift, you can calculate what your stall speed is going to be. So that same equation switched around and let you figure out all kinds of stuff.
Right, which allows you to kind of make sure you've got your envelope set right in your design.
Mhm.
So I've noticed you use that a bunch. You're like, okay, we're looking at stall. Here's what we're going to do.
Yeah.
Okay, now we want to do cruise speed. Here's the thing. Okay, and again, use that last equation we're solving for velocity, because you want to make sure you're not exceeding those envelope limits. But when you're trying to figure out, well, what airfoil do I use that coefficient of lift.
Oh, well, here's an
version of it,
example.
right?
You know, let's say we've already figured out our weight, our wing surface area, our dynamic pressure, and our coefficient lift. Let's say we figured all that out. You remember that number we were talking about a while ago, maneuvering speed, where if you're below that maneuvering speed, the wing will stall before you break it. So let's say we want to figure out what that maneuvering speed is. So we would take our weight, multiply by 3.8, because that's our load factor. That's what we would stall at. And then we already know our surface area, coefficient lift, and rho, so we can actually calculate what that VA speed is.
Okay. What the maneuvering speed is.
Mhm.
Cool.
Just by changing the weight part, because we're adding the load factor of 3.8.
And if you've ever looked into full scale aircraft, like one of the big things they test you on is do you understand all the V's, V sub whatevers?
Yeah.
V sub E, V sub A, what's your stall speed, what's your takeoff speed, what's your rotation speed, with all that stuff, because they're critical to the airplane you're flying. If you don't know those, you will get yourself in deep trouble pretty quick. So it's important when you're doing the design to understand what they should be. And then you go out and test that and verify that they in fact work the way you plan.
Yeah.
Hopefully on the bench before you can do otherwise. But yeah, that generally is the design process, right? You calculate it first, and then once you're certain that you're happy with what you've got, and you've already done the other tests, that's not going to break, and you go, okay, now let's confirm that these are in fact what they are. And then that's where the whole, if you look at experimental aircraft and stuff, they'll basically, somebody who's built their own or whatever, they'll either get a test pilot who goes out and will go and test those limits and just verify that they are in fact what they are, or if they're different, what's making that happen, right? They've got the experience to be able to get out of situations most of the time.
So the reason I want to bring this up is you guys that are building scale models can do the same thing. Let's say you want to know what the stalling speed of your airplane is going to be. In other words, or you could say at stall speed, how much weight can the airplane be? That's probably the more important thing. So if you're building it and you realize you're going to be too heavy, then you can, ahead of time start making changes. So if you've already designed your wing and you know what the surface area is going to be, and you decided what stall speed you'd like to have, it might be hand launched, or it might be, 20 miles an hour or whatever. And you used X-foil or XFOL R5 and designed your airfoil, you know what the coefficient lift is going to be at that speed. You can calculate how much that airplane can weigh to get that. And so that ahead of time, you can start, measuring your components, weighing your components as you're building them. You can say, oh man, it's going to be too heavy. Or you can say, oh man, I'm underweight. I can actually stall at a lower speed, something like that. Or reduce the size of the wing, or, whatever you want to do.
I know what a number of RC pilots, I'll call it what they tend to, at least what I've done in the past when I'm doing a design. Again, this is that, it should be about right. Kind of looking at it. Which is looking at the cubic wing loading, which is a non-scalar, we'll call it generic or generalistic behavior characteristic. Like when you do the cubic wing loading and you go through that that calculation, it gives you a kind of rough number, and it's like, well, it doesn't matter what scale it is. Those in this range behave like a glider. Those in this range behave like, a fighter, or or you better be doing aerodynamic or aerobatics or whatever that, they kind of tell you the general performance characteristics that you can expect from this thing. So at least it gives you a ballpark, but this gives you very specific information that you can hopefully use to verify what you've thought out.
Yeah.
Cool.
All right. Let's see.
Really cool.
Some other simple calculations that you guys probably already know. When we're talking about surface area, we're not talking about wetted area, which would be the entire area. On surface area is the area you can see as you're looking from above. It's called the planform area.
Okay.
And then I'm sure you've
Okay,
heard people talk about.
So not so much. Like if you,
It's basically if you cut your wing at the chord line, so it's flat. What's that surface area?
right, if you took the wing, look at it from above, and converted
Yes.
it into a 2D object.
Yes, exactly.
You're not getting the benefit of any kind of a curve
Correct. That's
that's
not being
occurring
included.
there. You're not getting around it
Right.
in those.
It's not the wetted surface.
Right. Because wetted would be entire top, bottom, tips, everything. So we're not talking about wetted. We're just talking planform surface
Well,
areas.
see,
You're viewing it
wetted
from
didn't
above.
mean a whole lot to me prior to these conversations. So
Yeah. Now, wetted area is something you use when you're trying to calculate drag. When you figure out friction drag, then you use wetted area.
mhm.
Right. Because all the viscosity of the fluid that you're going through is pulling on all of the surface it's in contact with.
Exactly.
Right. So you need to know how much surface is that, right?
So now some wings will be tapered or have odd shapes to it. For a rectangular wing, you can calculate the aspect ratio. For a rectangular wing, it's just the span divided by chord. That gives you your aspect ratio. But some wings aren't that simple. So the way you calculate aspect ratio for those is you square. Let's do this one here. So you square the span and divide by surface area, and that'll give you an aspect ratio. So you can completely ignore the shape of the wing, which is really nice for calculating the aspect ratio.
Oh, well, that makes it much simpler.
Oh, yeah.
Because if you're doing design work in some sort of CAD system, those are very easy to get. Those are very easy values.
And then this is just different rearrangements of the same equation.
Cool.
All right. Okay, so calculating surface area, though, for rectangular wing is really simple. But what if you got like a tapered wing? So you just use the trapezoidal equation. So you figure out what the average chord is, which is the root chord plus the tip chord divided by 2, and then multiply by your span, and it gives you a surface area. So that's pretty easy.
Okay.
Matt, I think I remember you covering that way, way back.
Well, that's when we're talking about. This is where I'm talking about the CG and all that stuff. A lot of this pertain to some of what we're doing there. It's not the same, but so when you have to figure out the mean aerodynamic chord, the max,
that's different.
That you got to figure where that is to figure out your 25% mark, and then that tells you where your CG is for the RC airplane, right? Like that's where we ballpark it at, right? We say, hey, if you don't know, then do this, right?
So I put this MAC and MGC in here because I'm sure people have heard about it, but and I talk about. No, I didn't talk about how to calculate the MAC. But what we just talked about, the root chord plus the tip chord divided by 2, that's the mean geometric chord. So that's going to be right in the middle. Now, your mean aerodynamic chord is usually inboard of that for a trapezoidal wing. For a rectangular wing, they're in the same spot.
Okay.
But I didn't put anything in here about mean aerodynamic chord because that you almost only use that when you're dealing with pitch, and I'm not talking about pitch today, so I decided to actually leave it out. But the equation for calculating the mean aerodynamic chord is a lot more complicated. But usually it's going to be just a little bit inboard from the mean geometric chord. At least on a trapezoidal wing.
Yeah. In RC, we don't care. I mean, because we're not needing, our lives aren't on the line, and we don't need to be that exact. What we found is that if you use the it's effectively the MGC, at 25%, it'll close enough where your plane will fly, and you can trim it out and get it so it flies the way you want.
Yep.
Without crashing it.
Yeah.
So, and that's really the and essentially when you went through your couch, you essentially do something very similar. If I remember going some of the episodes I saw of yours, it's you go through. I mean, it's a lot more detailed. But at the same point, we can go through that detail too. But for the most part, it's very similar, very very similar.
And in fact, you can actually calculate it reasonably easy if you have a wing that has multiple trapezoidal sections.
Mm-hmm.
Take a
Like
section by section.
Yeah. And then you multiply them by the surface area, and then sum them all up and divide by that entire surface area. So yeah, it's not too bad.
Yeah,
It's more
weighted
it's
average.
that's where spreadsheets come in really handy.
Yeah, right.
Oh, and by the
Amen.
way, I don't want to put this in here. If you see this lowercase lambda, Greek letter lambda, it almost always means taper ratio. So if you ever see that, that's usually what it means.
Okay.
An uppercase lambda usually means a sweep angle somewhere on the wing. It could be a hinge chord line, or the could be the 25% mean aerodynamic chord. It could be leading edge. They usually have to specify what they mean, where that capital lambda is, the sweep.
Okay. And then that's the ratio of the chord at the tip over the chord at
The lower one is, yeah.
Okay, good.
Some of these things I thought I'd go ahead and mention just in case you see them. You go, what is that? So maybe it'll,
Well, no, there's so many of those too. When you're going through all those equations and you're trying to learn about lift, you're like, what? We could use, well, you just add lambda. I'm like, well, what the heck is lambda? Oh, well, that's just CT some CL over X, Y, Z. You're like,
yeah.
Oh my God, where are these values coming from? So yeah, I appreciate it.
There's usually a standard usage of these letters. Like Q is always dynamic pressure. Lowercase lambda is almost always tip ratio. Occasionally you'll run across a report where they used it for something else, but usually that's what it means. A big C usually is a coefficient of some kind. A smaller C is usually a chord of some kind.
Okay.
So they're fairly standard. The one that really bugs the heck out of me is aspect ratio. Some people use A, which I hate, because in lots of math, A means area.
Right.
And so people could easily get confused and think you're talking about some area. So I always use AR.
Right.
Well, I appreciate that. Because, if you threw up a big A, I'd be like, oh, yeah.
Yep.
Right.
Oh, let's see. I went too far. So let's go back. Okay. So here's something that can be controversial, which is going from a small CL, maximum coefficient lift of the airfoil, to the maximum coefficient lift of the wing. Now, Raymer says just multiply by 0.9. That'll give you the maximum coefficient lift of the wing. I've seen other people say 0.88 or 0.85. So in all of Raymer's books, he uses 0.9. So, it's up to you to decide which way to go. 0.9 gives you more lift, so I usually go with that. There you go.
Dan Raymer's book that you recommend is Simplified Aircraft Design for Home Builders. It kind of goes through the process. It doesn't kind of. It goes through the process and gives you tips and tricks along the way.
Yeah.
And he really kind of outlines the general process. And more importantly, along the way, he says, now go do it. Like, don't just do what I'm doing. Do it do yours.
Yep. And he gives an example for his airplane. I think that book, the reason I decided to use it for the help, I won't say help build, but a way to lead people through a design process, is he actually does a pretty darn good job. Way better than any other book I've found so far for designing home builds or experimentals. I think he did a pretty good job. And he talks about outliers like canards, details. He mentions them. So I think it's a great
he also I mean, not that I've read a whole litany of book sets, but I feel like he not only just goes through it, but he talks about it in English, which is a big help, because a lot of the books that I've read are like they assume you know the lingo, and the lingo isn't always the easiest to pick up right away.
Yeah.
So, and go ahead.
So I decided
I just wanted to point out that that's what, when you're talking about Raymer, you're talking about this book.
Yes.
And any of his other work.
Or his textbook. Yeah, he's got a big fat textbook too. So I decided to go ahead and throw this in here. It's probably not relevant for a lot of modelers, but if you want to figure out how much lift your wing when you have flaps, let's say you build flaps onto it and you want to deploy it and figure out how much lift you have, there's an equation for doing that too. But oh, here's that big lambda right here. So
Okay.
and so here, this HO means hinge line. So we're talking about flaps. So whatever the angle of that hinge line is, you would put it into cosine. But most of us, I wouldn't bother doing it unless your angle is like more than 20 degrees or maybe 15 degrees. If you're less than
You're
that,
getting
I wouldn't bother.
a
You're close
really
to
small reduction. I mean,
yeah, exactly.
yeah, at a what 10 degrees, a cosine of 90 or a cosine of what would that be?
It's probably about
80.
0.95, something like
Yeah,
that.
you're getting 0.9. Yeah, you're
Yeah,
losing like 5%. It's almost
yeah,
insignificant.
yeah. So yeah,
You
and same.
you have to get past like 20 degrees or so.
Yeah.
15.
So basically, you're taking, yeah, I talked about it here. So basically, you're taking the coefficient of the wing without flaps, that says here, and then how much does the lift change on the airfoil? So lowercase coefficient of lift. How much changes it? Is there in the coefficient lift between flapped and not flapped? So that's what this delta is. Oh, that's a Greek letter delta, capital D delta there.
It's a differential or change between.
Yeah, that's all it is. And then you gotta multiply by this ratio here. So this is the surface area of the wing that is flapped divided by the entire surface area. So let me talk about that real quick. I made a little diagram down here. So here you can do the same thing with a semi-span. So there's a flap here and a flap here, comes clear to the center. So this entire surface area here, the portion of the wing that has flaps, divided by the entire portion. Now I'm doing semi-span instead of entire span here, so it's the same ratio.
Mhm.
So that's what we're talking about, that ratio. So you take that
And
ratio.
so in your example, you have 70% of it has
Yes.
flaps, and
Yes.
30% of the half chord has, or not the half span has is
Not
aileron
flapped. Yeah,
basically,
not
or
flapped. Yeah.
non-flapped.
Yeah.
So you're just saying that not all of this wing is going to have that flapped
Right.
delta
Right. So
of
for
lift.
this particular wing, that ratio is 0.7.
Mm-hmm. Correct.
Okay.
Yeah. But it's really easy to do for a rectangular wing. You don't even have to go the surface area. You can just do the flap span divided by the semi-span, right? Because the chord's the same. But if you've got a tapered wing, then you actually have to calculate that surface area that's flapped and divide it by the entire thing.
Okay.
Because that chord makes a huge difference. The bigger that chord is, the more difference it is. You're going to have a lot more lift because of a longer chord. That's why you need to take that surface area, take that into account.
Okay.
Because it wouldn't be the same if this was, if you had a tapered wing. Let's say this outside 70% was the part that was flapped. You wouldn't do that, but let's say it was.
Right.
So that's actually going to give you a smaller ratio because the surface area would be less.
Okay.
Okay, so yeah. So you do that calculate. Oh, you have to multiply that by 0.9 again, which is basically the same thing we talked about from maximum coefficient lift, that 0.9 there.
Right.
It's essentially doing the same thing, but for the flap section of the wing.
Okay.
And that gives you the coefficient of lift with flaps deflected.
Okay.
So, pretty easy to do.
Yeah, relatively speaking. It seems like a lot, but I mean,
Yeah,
when you break
well,
when
once
you
you
break it
start-
down, it's like, okay, it's a
Yeah.
ratio of the thing added to what you already know, or that portion of it. Yeah, let's go do it. Yeah.
So we completely ignored coefficient of moment, coefficient of drag. That was just, going to be too much to get into this too. But at some point, if you guys want to talk about that particular coefficient of moment, we can do another talk about that too. And then we'll start talking about the mean aerodynamic chord.
Well, it sounds
Yes,
like we
we
got material for the next time we.
At some point, if you want to, yeah.
Yeah.
Absolutely.
Drag is a drag, so we might skip that one.
But
I mean, Raymer goes over some simplifications in his book, at least for the full size airplanes.
Mhm.
Now, drag is different when you get down to those lower Reynolds numbers. Also, your air gets much thicker. It's more viscous. At least the flying surface thinks it's more viscous, so you get more drag. So it's different down there too. Yeah. You know how bumblebees have tiny little wings that are flat? They think they're flying in molasses. The
Right.
air to them is horribly thick.
Which is part of how they can fly, I imagine.
Yes, that's how they can fly with those really low aspect ratio wings.
Yep.
That are, they're horribly low aspect ratio, but that doesn't matter to them because they're flying in something super thick. It'd be like swimming in water,
Yeah. I guess
So you're telling me
never-
bees swim?
Yeah, they swim through the air. Yeah, pretty much.
Interesting.
Yeah.
You're blowing my mind here.
Okay. Now, here's the last section. This is the last part of our plan. So this kind of what came about because you asked me if I thought about making a scale version of the US4 ultralight airplane.
Right.
And I'd never looked really closely into this part of it. I'd looked in the Reynolds number issue and I said, I'm not going to design an airplane that flies 4 times as fast for a quarter scale model. That's never, heck with that. But when you go to ignoring that part of the issue, you can actually do some interesting calculations and set some ratios so that your scale model will behave similar to the full scale as far as dynamics go.
Okay. And that was
Especially
leading to the question I have to talk about is how
so
is it when we're flying our scale models, we experience a lot of the same characteristics, that I hear full scale pilots talk about with the plane that we have a model of. They're like, oh yeah, this thing's a beast, blah blah blah, and then talk about the characteristics. I'm like, my scale model is the exact same thing. Like, how do you know that? I'm like, I'm telling you, it flies the same way. I can feel it. And they're like, how do you feel that? I'm like, look, you could just feel it.
as long as you use the right ratios, you can get similar performance.
Okay, so tell
especially on the dynamic behavior. That'll be things like how fast it can roll, yawing tendencies, things like that. Yeah, absolutely.
I mean, those are the ones we kind of feel as pilots, right? So yeah, tell us more about it.
Okay, so again, this came from Horner. When I started looking into it, I thought, man, where can I learn more about this? Because I knew about the cubic equation you're talking about, but that kind of gets you maybe in the ballpark. But what if you want to have a more assurance that you're going to get similar behavior for a scale model? Now, if you don't care about that, this won't matter at all. But if you want to try to get similar behavior, like like some guys who are trying to build scale models first before full size, then what you want to do is set the coefficient of lift of the wing the same between your full size and your scale model.
Okay,
so let's assign our coefficient of lift. Let's just say it needs to at least be proportional. So we have a full size equation over here for our lift, our coefficient lift, and our model size over here. Now, some things cancel out. The 1/2 will cancel out, and our air density. Let's just cancel those out, okay?
Because they're the same no matter what.
Yes, exactly. Now, we can rearrange that into ratios. Like we can take our weight of our full size and put it over here. We can take our surface area, put it over here, and move things around. And we get this equation down here. So this is ratios. So you got your surface area ratio of your wing, you got your velocity ratio squared, and you have your weight ratio. So as long as this ratio multiplied by this ratio equals this ratio, and what I'm circling is the velocity squared multiplied by the weight squared equals the surface area, as long as that's true.
It's a velocity ratio squared times the weight ratio squared equals the surface area.
As long as that equals
squared.
Is this a typo here, by the way? Velocity full scale over velocity.
Okay, here's something that's a little bit confusing. So this is model over full, this is full over model, and then model over full.
Okay.
And I assume that's just the way the equations work out.
Right, exactly.
Okay,
so because I put weight and velocity on one side, and you'll notice weight's above velocity. So so when you
gotta multiply it.
Yeah, exactly.
Multiply and then divide. So they flip.
Yeah. So weight velocity m will be below weight m, and then vice versa. That's the way it turned out there. And that's confusing. I thought about trying to figure out a way to make that less confusing, but I didn't come up with it.
No, it's fine. And then for clarification, when you're saying the weight, is weight squared?
No,
Or
weight is not squared.
okay.
No.
'Cause
Only velocity is squared.
So we were saying velocity squared times weight squared, but weight is not.
Oh,
being
I'm
squared.
sorry. I'm sorry.
No,
I
it's fine.
misspoke.
I just want to
Yeah.
clarify that.
Yes, you're right. You're right. Weight is not squared and surface area. Well, I was going to say its surface area isn't squared, but actually it is, because that's unit length times unit length, right? Surface
Right,
area
but
is
you're not
squared.
squaring the result of
You're
that.
not squaring the square. Yeah.
Right.
Yeah.
Yeah, we got you.
Okay. So
Okay, so did you look at a quick example, for example, like a Piper
yeah, we
Cub?
do have an example. Yeah. Actually
Oh,
went
you're
through
the
the
best.
equations. Yeah.
Look at
So
you.
as long as this is true, your dynamic behavior of your scale should be roughly correct.
Right. It'll behave in similar manners.
Yes, exactly.
Go ahead.
Now, if you're outside
I'm
of that, doesn't
really
mean it
curious.
necessarily won't behave similar, but you're more likely to get good behavior like this.
Right.
Mhm.
Well, I mean, it'll create a meaningful parallel. So if you were looking to see how does my model that I want to build full scale going to fly, you pay attention to these ratios,
Mhm.
and the model you build should inform you as to what you can expect. Okay, go ahead. He's nodding.
Okay,
Go ahead.
now here's where things start getting more confusing, I think. And I think part of it's just because of some things are squared and some things aren't.
Sure.
So keep in mind that when we're changing the linear scale, let's say we want to go to 1/4 scale, your surface area is going to be 1/16.
Mhm.
Right.
Yes.
That is
So
something we
four
discuss
four
all the
squared.
time. You're like, "Oh,
Yes.
it's only a
Yes.
quarter." Like, yeah, but
Yes.
your wing surface that's creating the lift is
Yeah.
significantly
Well,
less.
so if you quarter to scale, you're quartering if we're looking at it from a 2D perspective, top down, you're quartering your width and you're quartering your.
Right.
Yes. Yes. Exactly. So you got to keep that in mind. So that's not a linear ratio.
Relationship. No, it's an
Yeah. Even
exponential.
though L over L, model length over full size length, that's linear.
Yeah, but it's
But
in both
but you
directions, right?
got to square those, so it's 1/16 for a quarter scale.
Mhm. That's important.
Now weight is tricky. Um, Weight is usually volume, not always, but usually volume. That's the cube, not the square. Volume is cubed.
Mhm.
So if
Right?
you go if you go 1/4 in scale, your volume is 1/64.
64th, yeah.
Yeah. So, but in reality, airplanes aren't solid. So it's somewhere between a quarter and or it's somewhere between squared and cubed.
Okay.
So somewhere between what, a 16th and a
64th.
64th.
Yeah, in
Yeah.
this example, yeah. So
Ballpark in that wide range there.
yeah. Yeah. So I did an example here, and I'm using the UW4 as an example. So the stall speed's around 28 mile per hour for an ultralight.
Mhm.
And let's say I want to make a quarter scale model, but I want to be able to hand launch it, which is going to be somewhere around, let's say 14. It's a ratio of 2, which is kind of nice. So that's why I picked that.
Yep.
So
Thanks.
our velocity ratio, not
Yep.
squared yet, is 2. So we already determined that. We already determined our length ratio, 1/4 or scale. So we know that our surface area is going to be 1/16. So we
Right.
can start plugging some numbers in here. So what I've done here is I've changed things. I actually took the square root of this equation up here. I took the square root of this equation up here. So that's going to be, instead of, surface area squared. So if I take the square root of that, it's going to be length over length, right? So it's going to be 1/4.
Okay.
That's our scale. Taking the square root of a square just drops out velocity over velocity. That's what it becomes, right?
That's
And
even.
then we're going to have the square root of our weights. So that's a little bit easier to deal with down here. So I start plugging some numbers in here. So length over length is 1/4. Our velocity ratio is 2. So all we got left to figure out is our weight ratio. And so we start doing
Right.
some multiplications down here. So now, now this is a little bit confusing. Now I went back and squared it. So I squared the 1/4 that was there. I squared the 2 and brought it underneath. So that's this 4 here.
Okay, so he's
And
doing some tricky, well, I'll call it tricky,
yeah,
but he's doing
yeah,
some
doing some
algebra there.
algebra. Yeah,
Okay.
I do a lot of algebra. I've actually had to do calculus one time. That was annoying because I had to go get my book out and remember how to do some formulas.
That's how I do it. Like,
Annoying.
and I'm like,
So-
okay, so Spike is filling up an airplane with a horizontal cylinder.
Yeah.
X amount of gallons per minute. Okay, forget it.
Okay, so I condense that down. That just becomes 1/4 cubed.
Okay. Is the 4
And
cubed?
so, yeah, the 4 is cubed. Yeah.
Okay.
Well,
got it.
you
Yeah,
can
so
cube the 1 too,
164.
but it's 1. You know.
Okay, got it.
Yeah.
Yep.
So that becomes our weight ratio. Then becomes 1/64. So if we design our wing to be, let me go ahead and give some other numbers. We figured out our ratio. So our gross weight of the ultralight, let's pick 454 pounds. So that now we can figure out.
So
1/64th of-
454, right, comes from you have 254 is your limit plus a person
170-pound person and 30 pounds of fuel.
and 30 pounds of fuel, right?
Yeah.
Because you have a maximum of
that was
5
one of
gallons.
the things I forgot. Yeah. We can only have a maximum of 5 gallons in an ultralight of fuel.
Yep.
Which is
Even
really
though,
annoying.
even though, boy, it sure could take long more than 5 gallons, but
Yeah, especially with the 2 cycle. Yeah.
yeah.
Okay.
Anyway,
So we do our 454 pounds. Oh, I got a mistake here. I should say 64.
okay.
But you get somewhere around 7 pounds for your ratio, or for your quarter scale airplane to get similar performance. So it's other than dealing with the squares and square roots up here,
Mhm.
it's not too bad.
No, I mean it's pretty straightforward for what you're aiming for there.
Yeah.
On.
So if I wanted to make a scale version of the UWS 4, which we talked about, quarter scale is probably what I would do. And I would probably increase the speed a little bit. I actually might go up to 28 miles an hour for a stall speed, which would make it
That's
so that I
not
can actually have.
unreasonable.
So
That's
if
not
I
unreasonable for an RC plane.
yeah, so if I do that, that'll actually increase my weight a little bit. So that'd be nice.
Honestly, for what we have, I'm trying to think. Quarter scale. What's the wingspan of your plane? I can't remember.
About 23 feet.
Okay, so 1/4 that would be 6 feet.
Yeah.
Ish.
Yeah.
That's actually. I mean, that's what this guy is over here, right?
Mhm.
So I mean, so I could see building your plane as this quarter scale model,
You
and
could.
it easily being at 7 pounds or under.
Yeah.
Except I could fly it for more than 40 minutes. 'cause-
Yeah.
Just kidding. I'm busting. I'm messing around.
No, you're right. Absolutely
Let's see.
right. Yeah.
Yeah,
But
I'm
that's-
just saying if we did that, yeah, it would probably come in about probably be about 7 pounds. It's probably reasonable.
Yeah. So you actually asked me about materials one time.
Mhm.
What would be the difference between full size and scale? And really, the thing that drives it is going to be your weight ratio usually.
Yeah.
And it also has to deal with the behavior of beams or thickness of material.
Okay.
Now you mentioned that you had been going through Stress Without Tears, right? It was the structural analysis stuff.
Yes. Yeah.
Yeah. The when you change a material from, let's say, 1 inch to ½ inch, you don't just half the bending load that can handle it. It's way
Right.
less than that.
Yeah, you
And
change the
so
moment of inertia of the material
exactly.
significantly. However, if you're doing a monocoque design, it's
Yeah.
But I'm with you. Yes.
And so when your weight, if you just go, let's say you want to, let's use aluminum as an example. Let's say you do a skin of on full scale, I can't even say it, full scale size of 16,000. So that's what I'm going to use on the Universe 4.
Okay.
If we knock that down, it's going to be 1/64th of that. No. Well, the volume
Okay.
would be 1/64th. So square.
Okay.
So it'd be a quarter of the thickness. Well,
Right.
we're talking really, really thin aluminum then.
Yeah, it's really thin.
And
Yeah,
it's not going to bend the same. In fact, it's going to be much weaker.
A little bit thicker than aluminum foil, right?
Yeah. So
2 or 3
you're
plots.
talking really, really thin, and it's not going to behave the same. So you can't take the
No.
same materials usually at scale and use them, or at full size and use them at scale. You
Okay.
almost always have to use something with lower density.
Okay.
So that's basically what I'm saying here.
Well,
She
especially
almost,
if you're gonna capture the weight ratio, right? Yeah.
yeah. So I went through a few examples here, but it just boils down. You're almost always going to have to use lower. For example, let's say you want to duplicate the structure. Um, you would probably use something like styrene.
Right. Yeah.
You know, so in place, like you want to build all the aluminum parts, but aluminum that
Yeah.
thin,
I
just
just imagined,
so.
taking a little like little light squares and like hydroforming them with a
Mm.
sandbag and just squish.
Yeah,
Just put them in there, squish, 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 squish,
yeah,
squish, and get a bunch of those, and then attach
yeah.
them to like an aluminum tube, which would be
So
your spar, but it would for us it'd be really tiny.
yeah, so almost always you're going to have to pick some material with a different density. You almost can never use the same material for scale and full size.
Okay.
I won't say always, but a lot of the time.
No,
Yeah.
that makes sense.
Yeah. So
So
that's all I really had, guys.
that
Well,
that was it. I mean, it was only like all the details is great.
yeah,
No,
that was only blowing my mind 100 times. Thank you.
And that's the thing, Joe. It's like and again, if anybody listening to this here, if you have not hopped over to the Ultralight Airplane Workshop YouTube channel, go listen to Leon explain all of the things in the same kind of detail. It's really it's really helpful if you're truly looking to understand what's going on behind all this stuff because it go through it all, but you also explain it along the way. You don't just kind of go, it's just over here. It just works.
and I usually do a better job on video because I'll say something, say, that's confusing. So I'll think about it for a while and, oh, this
Yeah.
sounds better.
Yeah. Well, yeah, I mean, right, we're doing this semi live, but
Yeah.
we're not sitting there recording like 600 times. So, there is an advantage of being able to do that with your own videos, right?
Yeah.
So cool. No, this has been super helpful. Joe, did you learn anything here?
No. Yes. This whole episode was me just trying to take enough in, but no,
Well,
it's
if you had done lift of wings, you would have had to do all this. So
Yeah,
well,
probably.
no.
just like you researched the previous one on aerodynamic lift, you would have had to research all this. So
Yeah. Well,
That's why we bring in guests. You guys have already done all this. You kidding me? No, no. I really appreciate that you've gone through this trouble to kind of look at what it means and how can you because that's kind of the thing. Isn't it the point of like, well, we want all these scale models. One, because we like the look of the plane that we're trying to put in the
Mhm.
air and we'd love to be able to fly it. But, part of it is that imagining that you're flying that plane, like you're in
Mhm.
that plane and this is how that plane flies. And that kind of, I'm having a similar experience that a full scale pilot would get.
Mhm.
Right. Like that's part of what some people really thoroughly enjoy about the hobby. And so, if this can help somebody kind of get like, oh wow, this if I just tweak a couple things here, right, I can make sure that I'm getting not make sure, but I can hope to have a closer experience to what a full scale pilot would do. And again, if you're also looking to do designs, um, I know that if this thing works this way and I want to scale it up, well, I can use that to help me understand what I need to do to go ahead and get it a little bit bigger or a lot bigger or whatever it is I'm aiming to do.
it makes me wonder if we ran a bunch of numbers on the Noob Wonder and the Giant Wonder, like
Oh, we should.
what kind of
Mm,
similarities or
yeah.
differences would we see in the numbers now? Because the Giant Wonder was super floaty,
Oh man.
where the regular Wonder is not. It's not that it flies well, but it's not floaty the way the Giant was. But the Giant
Right.
was also very light in comparison,
Sure.
Yeah.
So
for
that's
its
where your weight
size.
ratio comes in. Yeah.
Hmm.
Yeah. Definitely.
Yeah.
I know when I did my cubic wing loading, I think the original one is set square in the sport flyer, right? Reasonably so. But when I did the wing cubic loading for the 300% version of it, it ended up somewhere below like glider. It was like you may have a hard time keeping this in the air from the wind gusts. You gotta be careful.
Yeah.
And it's like, oh, okay. Even at 10 pounds. I mean, this thing had a 24-inch wing chord and a 9-foot span, 10-foot span, somewhere in there. So it had a pretty good area. And again, it's 10 pounds, which for that size is almost nothing.
Yeah, that's a low
I don't,
wing
Joe.
loading. Yeah.
It was kind of heavy to lift and kind of get started.
Yeah.
Is what because you could feel the weight, but the second it lifted, I mean, I didn't feel like it was dragging at all. It wasn't like, oh, I can barely get this in the air. It was like, nope, off we go. I mean, it's just that gentle push was enough to give it the lift to get moving. So yeah, it's pretty neat. It was just really cool. Like, and that's part of what spawns all this is like, we tried this thing. We didn't know nothing about it, so we just tried it. And some of the characteristics I think both Joe and I saw when we flew the large one, because we both flown the little one, we were really surprised at kind of what we were experiencing. On top of me maybe not balancing it perfectly for Joe, and it was kind of
I mean, all that aside, like
yeah, but you could tell almost
seeing the equations and having you, Leon, explain all the things that go into it and how changing the things that in that case we changed, but changing the things that someone may want to change in doing their model from a full size, or it's eye-opening to see how those numbers come together.
Yeah.
Right.
Even in more of a even in just a presentational theoretical point is like, okay, if I were to start plugging numbers in here to get final results, like it's gonna be all over the place. It's gonna be wild. So thank you.
Use spreadsheets. It makes it so much faster. Make far fewer mistakes.
Final tip of wisdom: use spreadsheets. Lots of spreadsheets.
What's funny is I work in IT, but I have a love for spreadsheets, specifically making them do a thing that I want done. Unrelated, but we've got phone numbers that we're having to go through, and is this person with our side of the company, what department are they in, this, that, just how are these phone bills going to get billed out? And I exported our entire Active Directory, which has all the users in the and then grab that, put it in another sheet, and just started using VLOOKUPs and comparisons and this, that. So love spreadsheets. And they are little customizable programs that you can do amazing things with if you take the time to learn how to use them.
Yep. Just when you're doing calculations, be careful that you're carrying the right numbers and that they're in the right units. Because there's a lot of calculation programs that I use that they check units because you put units in there. But spreadsheets don't. You just have to be careful. But once you do, once you've checked it and it works, you got the thing. Boy, oh boy, the world, you can check all the things and quick too. So
one of the things you need to be a little careful about, even if you're using a calculator, is sanity checks. Actually kind of know ahead of time roughly what the value should be. And if it's not that, you need to start going back and figuring out if you did something wrong.
I was just saying, one of the things I'll do when I start running numbers is I try to have as many numbers as I can separated out and have my formulas construct from those.
Right.
And then plug in some known value. This is the area the answer should be within.
Right.
And if it's way off,
good advice.
Go back to your formula.
Oh, yeah. Like on airplanes, I know that at least for ultralights, the wing coefficient lift at cruise should be somewhere around 0.5. And if it's saying like 2.0, I know something has gone wacky somewhere. So, having a good idea roughly what numbers you should be seeing is it's necessary. In fact, I had a video one time where I didn't do a sanity check. I did a calculation and I said, I didn't think about it enough. So I made a video about it, published it, and then I'm going back through a couple days later, I'm thinking, that number makes no sense. And so I went through it again. I said, oh man, I made a mistake.
Yeah.
the nice thing about RC, taking it a little back home maybe, but RC and then what you're is we can do the things at RC level before moving into more of a proper scale or into the fuller size stuff. We can play with and experiment and fail at our level
Mhm.
and learn from that, because the failures are where we learn the most, really.
Oh yeah,
And
absolutely.
then what you've learned then apply to. So some, like I think you were saying, like you ended up going into it, but take me. If I were going to, I've been playing with them with RC airplanes and such. If I wanted to move into a aircraft design or build something bigger, there's a lot of stuff that I've learned from the failures of what I've done here that I could carry over into that. But even
Mhm.
just in the hobby in general, it's okay to fail because you're going to learn from it. I guess I should clarify. It's okay to fail so long as you learn from
Yeah.
Yep. So that brings us, I guess, to the question you were saying, kind of, if you're to take a full scale show. So one of the listener questions we have a couple listener questions, was how do you get started with ultralights? How do you get started building, and then maybe how do you get started designing? Because they may be very different answers. So,
Mm. Well,
or if you
building is
had any
easier.
tips.
Um, it, it, it for building, it kind of depends how much time you want to put into it.
Okay.
Because you can get uh, kits that have all the holes drilled for you. All you need to do is deburr the holes and line them up and stick in rivets. And that's the majority. That's aluminum, of course. Um, so there are some that are like 400 hours. If if you think you can stick with it for 400 hours, you can have an airplane.
it.
Hmm.
Some of them that are like the Aerolite 103, which it comes with sailcloth already sewn. It comes with tubes
Hmm.
already drilled, and in that case, you're not hardly doing any rivets. You're just bolting tubes together and put the sailcloth on. That one I think is around 50 to 75 hours assembly.
Okay.
Um,
That's a
so
that's a mean
it,
week.
it,
That's
yeah, it depends. You got to decide how much time you're willing to put into it, and then start looking for an airplane that has the right number of hours for you.
okay.
Some people have spent 10 years building it, off and on, in spare time,
Yeah, I think that's right.
experimental airplanes, especially wood.
Sure.
Wood takes forever to glue and nail and wait for the glue to dry, and especially if you only have one jig. Um,
Mhm.
Yeah. Yeah, I
so
imagine so.
yeah, but fortunately,
Yeah,
this rib will be much faster when I do hydroforming.
I know we've got one of our members, 10745. He's he's building his own uh, airplane from
Mm,
scratch. I
yeah.
don't think it's an ultralight, but he's building an old wooden jobber.
So building from plans is going to take you the longest.
Yeah.
Because you gotta cut everything yourself,
Yep.
deburr everything yourself, if you're doing metal. In fact, you're almost always gonna have some metal. That's the other thing, the materials used. Some people are very comfortable with wood, so they'll do an all-wood
Hmm.
airplane with fabric covering.
Yep.
Some people know how to weld, and so
Yep.
they'll do a steel welded, or steel tube fuselage, maybe aluminum wings if you're fairly comfortable working with aluminum.
Hmm.
So that also will help determine what kind of airplane you want to do, the materials that you're more comfortable with, or materials you want to learn about. Let's say you want to do
Right.
composites, but you've never
Yep.
done composites, So
It's go time to go and give it a try.
yeah.
I think he was last I saw he was there. It is. Back in the end of the year, he was welding a fuel tank together.
Aluminum fuel tank, yeah.
Yep. Yep. For his anyway, so
So
good.
you
I
mentioned,
appreciate
okay,
that.
so what about getting into design then?
Yeah, yeah. The other half.
I think that Raymer's book that you held up earlier,
Hmm.
the Simplified Aircraft Design for Home Builders, um, I think he does a better job of filling in the gaps than almost any other books like this one and
Yeah, they all seem to. I mean,
some
they have a focus and they do well on the focused area. But the problem is if you're trying to understand the whole, um, you have to pick up like 6 books and read them all
Yeah.
through and find out where they connect.
Okay,
Uh,
so that's the aerodynamics part of it.
yeah.
So that's only probably a third of the way through. The work that you have to do for structural design is
Mhm.
really, that's the most important part because, your plane will either break or not break based on what you do there. Um,
Right.
that's one of the things that really bugs the heck out of designers, especially when they're someone's building by plans. People always want to modify. They want to do
Mm,
things different. They say, I think this is a little bit too weak. I'm going to make it stronger. But then by making it stiffer, they're liable to cause something else to break because it's designed to have some flex, and then
Yep.
and
Yeah.
so that's it's something that drives designers nuts when people want to make changes.
Yeah.
Well,
As a
by making something stiffer, you're shunting the.
Yeah, you're moving the load somewhere else. Yeah.
right. It's
Um,
it's understanding where it's going to go. And
yeah.
it always goes to the weakest, but if the weakest isn't ready for it, you're in trouble. So,
Yep.
so as a follow-up, I mean, I'm sorry, if you're set, the follow-up with that is, let's say you have one. How do you get instruction and where do you go to fly?
Oh, that is tough now. The FAA has really messed that up when they took away the training exemption for ultralights.
Right.
Um,
That's what I
you,
thought.
you you can find instructors. It's much easier for powered parachutes and trikes. So weight shift um,
Right. Yeah.
um, wings. It's harder for 3 axis, but generally what you're gonna have to do is find someone who has a 2-axis version or sorry, not 2-axis, a 2-seat version of what you want to fly, like a Kolb. You can get a 2-seat version or a
Yeah.
single-seat version of a Kolb. So you gotta
Right.
find an instructor who has or can has access to a 2-seat version, train you in that because the aerodynamics will be similar. So that's really the best thing to do. And you can go to the Experimental Aircraft Association.
Yep.
Uh, Usually they'll have a list of pilots or instructors you can find. Um, Trying to find one for ultralights can be a challenge. You almost, depending on where you live, you may have to travel. You may have to go drive a few hours to find someone who'll do it, especially in the plane that you want to fly in.
Right. And all I can say from already starting my pilot's journey, right? And I know, Leon, you've taken piloting lessons and at least
Yep.
gone somewhere down the path,
Yep.
probably about as far as I have. Um, you need to practice.
Hmm.
Your life isn't in your hands. If you go up and thinking, "Oh, it'll be easy. I'll totally know how to land," get lessons. Get lessons.
Yeah. Yeah.
You even if you do nothing but fly ultralights after that, and you don't go through the whole deal or whatever, but for the love of goodness, learn how your airplane behaves, learn how to fly, learn how to land, learn how that
The
works.
Here's the probably the most dangerous thing is if you don't get training, you probably never practice stalls. You probably don't even know that you should practice stalls, so you know how to
Mhm.
get out of them.
Right.
And if you stall within about 300 feet of the ground,
That
that's your
might be
last
it.
flight. Yeah.
Yep. That's very
So
likely it.
I think training is very, very important.
Yeah. Yeah, unless you get your musher.
Yeah. Well, even then,
Yeah.
you're going to hit the ground pretty hard,
No, yeah, you will.
but you're
Gotta
liable
beat
to
that.
survive. But that'll be the end of your airplane.
Yeah, it sure will be.
it,
Okay,
it,
so well, go ahead.
Go ahead. Nah.
No, no, you sure?
I was going to say it depends on the design of the airplane. Like the
Sure.
Yildiz 4 is actually going to have some crush area below the
Uh-huh.
seat of 6 inches of aluminum to crush if you hit flat. Of course,
Right.
the gear will have to give out first
Right.
and shoot through the wings. So that'll take up some of the impact. But now I got six
Yeah.
inch of aluminum crush area underneath the seat.
Right.
So that'll help take up some of the impact too if you
You
ever
know, I would
hit flat.
never have thought about.
Yeah.
No, that's a critical piece to.
Yeah.
So, yeah, I mean, when we do building design, building envelope, design it to fail. It's gonna fail, but if it has an
Yeah.
exit, like if it has a path for it to fail,
Hmm.
so that the loads don't go, and
Yeah.
yeah, it's important. It's an important way to think. But same with structures. A lot of the towers, their weakest point is like a third of the way or fourth of the way up. Part of it is how the loads and the structure work. the structural capacities are linear and the loading is exponential. So the where they come closer, the capacities are, I think I got it backwards, but but basically they overlap at like the third point. So that if it fails a third of the way up.
Okay.
Which good news is that means when the top 2/3 topples over, it's barely gonna it's gonna hit the ground, but it's gonna be very close to the
Right.
thing. It's not gonna land like a tree dead across the whole, whole forest or wherever it's at,
Yeah.
across the roadway or whatever. So it fails, and you got to look at failure modes.
Oh yeah, absolutely.
So and that's it doesn't no different here, right?
So,
So
I guess the other thing about failure, landing. Let's say you have an engine out, especially two cycles are notorious
mhm,
for failing.
yes, they are.
Um, Frequently, at least in this part of the country, here in Kansas, if you're flying during the summer, you're going to be over a soybean field, and so the soybeans are about 3 feet high,
Yep,
and so they're going to grab your gear and you're going to flip over.
yep.
There's almost no way to avoid it.
And they'll take your shoes with them.
Those soybeans are tough. They do not tear. You're not
No.
going to just go through them. You're going to
Well,
stop, or at least the wheels are going to stop, and the rest of the airplane's going to go on over. So,
uh-huh.
you mentioned this before. You need to have some rollover protection on your airplane. Now,
Mhm.
it doesn't have to be overly strong because you're going to be slowed way down when you hit those beams, and you're going to go over probably not too fast, but you need to have it so your head doesn't get crushed when the
Right.
ultralight rolls over. Now, most ultralights are high wing, and so you've already got some rollover protection because it's going to roll over on that wing.
Right.
Um,
And
but
not
mine's a low
entirely on your head,
wing,
but
so
yeah.
I did that rollover test to make sure I could crawl out if it did
Yep.
roll over.
Yeah, it's a good
Yeah, yeah,
I really like that episode a lot. It I just there's a lot of things about that episode I
yeah.
enjoyed, and then part of it is like that eye on safety. The other half is how do you what are the things you're considering? Because you talk through all the considerations. You don't just say, oh, well, I did it because they told me I had to. Like
Oh,
no,
yeah.
yeah, I mean no one then there isn't one that tells you you have to. But at the same point, you're like, well, I thought it might be a problem, so I just went with the go kart thing, and we're good. Like no, you're like, no, I need to figure this out. Like this is going to happen this way, this way, or this way, and I need to be clear that
Yeah.
I'm good.
Well,
Which is pretty cool.
hitting soybeans is actually another good example because you're going to slow down really fast. If you've got your instrument panel here, you're going to smack your forehead into it. You
Yep.
want to have it out where it's about finger length away, so you can touch it,
Mm,
change things, but you're not going to smack it with your head. Or
right.
if you have a control stick, you want to make sure that your shoulder harness is situated so that your head can't go far enough to hit that control stick.
Right. That good way to think of it. Nice.
Yeah.
All considerations I would have.
Right. Yeah. All right. So we have one last thing for you, Liana. We're
All
gonna
right,
let you get out
let's
of
do
here.
it.
We really before we get too far, we definitely both thank you so much for joining us today
You're
and
very
teaching
welcome. Well,
us
thank you
so
for
much.
inviting me. It's been a lot of fun.
Uh, it was a lot of fun. I appreciate that you joined the community. You get to talk airplanes all you want. You know
Hmm.
that.
Yeah.
Okay, so we have a tradition here. It's called lightning round, where we're going
Oh,
to ask you a bunch of 10 really quick,
oh,
ridiculous questions.
okay.
We want you to come answer the first thing comes to your mind, whatever it is.
42.
Okay, well, we got
Solid answer.
9 more. No, but we're going to ask you this or that kind of question. You just
This is
answer
that.
whatever
Okay.
comes to mind.
Okay.
Yep. Okay. Joe, you want to start?
Do you want an explanation too, or just the answer?
Usually just the answer. I mean, if you
Okay.
want to go with
No,
do an
no, that's
answer,
good.
If
it
That's
you
gets
fine.
feel the
pretty
need to
long.
explain, go for it. Matt,
Okay.
you can go ahead and take it.
Okay.
Okay. Sit or stand?
Sit.
Tight grip or loose grip?
Tight.
Wood or aluminum?
Aluminum.
Silk and dope, Oracoat or other?
Oracoat.
Weight shift or airplane controls?
Actually, let me change that last one. Ortex, I think is the right one.
Or tech? Oh yeah, I'm
Yeah.
sorry.
Yeah.
That's my fault.
Yeah.
I should know
Thanks,
better.
Matt.
I know. That's all right.
Sorry.
I'll take that one right here, right on this shoulder. It's broad enough. I think I got that one. Weight shift or airplane controls?
Oh, 3 axis, definitely.
Okay. Trainer, low wing. Trainer or
So
low wing?
Mm,
I guess we could have
trainer.
said mid wing too, but
Yeah. I prefer high wing, but yeah.
Okay.
okay.
Yeah.
High wing, low wing.
Yeah.
let's see. I said forming or composites.
Say it again.
I was thinking like hydroforming, I think, or composites.
Hydroforming, composites. Yeah.
Okay.
Okay, wet layup or vacuum bagging?
Vacuum bagging.
Sunrise or sunset?
Even though there's so much trash with vacuum bagging.
Oh man,
Oh
yeah.
my gosh, yeah.
Yeah, that's a whole separate subject.
Sunset, because I hate getting up early.
Honestly, for me, it just depends on which direction I'm driving.
Yeah.
Well, I figured if you're flying, they're flying for a reason, right?
Yeah.
True. World War One, Golden Age, II, or Jet Age?
Oh, that one's tougher. There was so much advancement going on during World War One. I would actually prefer a third answer, which is World War II. So that's right before Jet Age.
Yep.
Yeah. Yep. Oh yeah. We do a lot of histories on the World War II because it seems to be where a lot of people's interests go.
Yeah.
And the last and probably most important question: creamy or chunky?
Creamy, just because chunky hurts.
And does your answer change if you add marshmallow fluff?
I'm sorry. I'll tell you why I'm laughing.
I think we broke him.
I think I'm broken.
I was gonna say, where's it cherry fluff, like Lee suggested?
Cherry fluff. I missed that one.
What?
If you go into the general channel at the very bottom, Lee added, "Well, what if it's cherry fluff?" And then he has a picture of cherry fluff. I didn't even know that stuff existed.
Cherry fluff. I don't even know what that is.
Yeah, it's apparently a deli serving thing. It's cherry fluff. I guess cherries in fluff.
Oh, like cherry on top of whipped cream?
Yeah.
Something like that?
No, cherry in fluff, like
in
marshmallow fluff.
Really?
Yeah,
oh, okay. I got you.
Yeah.
Okay. Wow.
Well, anyway. All right. Well, I appreciate you bringing us with this ridiculous.
It's fun.
I hope it was fun. So why don't you, if you don't mind, why don't you list for everybody where they can come find you, where they can learn more about Ultralights,
Absolutely.
learn about what you're into, what you're working on there, and then hopefully they can join your community. You have your own Discord community, which obviously they're dedicated to Ultralights, but it's another good community about aviation.
So the community is actually private unless you have an invite, but you can get that on almost any of my videos. There'll be links to just about everything there. So I have a website, which I don't work on too much, but it has a books page there that I like to use, books I'd like to use. Some of them are you can still get from Amazon. Some of them you can't get anymore, but I like them. So if you ever find them used, it might be worth getting. I do talk a little bit about some of the projects I need to go update the status of the universe for. I do have an X account, which used to be Twitter. And there's a link to that in any of the videos. I have a Facebook page, but I don't use it anymore. I got annoyed with Facebook. The YouTube channel. So that's Ultralight Airplane Workshop, or you can do it by @designer103, which is also the tag that I use on Twitter or X.
Excellent.
Yeah.
Good. Excellent.
I also provided a link to the archive of the Fluid Dynamics lift by Horner from 1985. And which is so
that's the lift one. So that's the second edition, which is the better one. It's got corrections. The drag book, I think, also a second edition. The first one was in 65. I was going to say more about the book, but it doesn't matter. But you get the latest edition if you can.
Yeah.
And by the way, they're hard to find in paperback. Very hard. I'm sorry, in hardcover. They're horribly expensive.
As a matter of fact, I just found the link to the drag one as well. So I will. It looks like 1965 version. So it may be if there's a more up to date version, you may want to find that.
Yeah, I think 65 is first edition.
Usually with those kind of, if you're just trying to understand the concept, though, like what goes into it, what's behind it. It doesn't
usually
really matter.
It's just math corrections for the second editions of those.
Right. Yeah, that makes sense.
Yeah.
Well, good. So I'm going to put a link to that as well. So that way
Yeah.
it's
But Horner, if you're really interested in aerodynamics, he went, like we said before, he went through and collated so much research and put it into nice description, nice diagrams. I find all kinds of answers there whenever I think, man, I start doing researches, I go through
Yeah.
the NACA report library and I think, let's just go see what Horner says. And he almost always has the answer.
Well, one of the things that started me down the composite path is looking at those Arnold videos. The
Oh
Arnold
yeah,
aircraft
the
maker,
AR5, yeah.
right? And he made a number of his build video, well, the
Yeah,
TED talks
some
that he had,
construction. Yeah, yeah.
right, and construction videos and stuff.
Yeah.
He made sure that before he died, I think he realized he had cancer. He put them and made them public on YouTube, so anybody who was interested could at least get a path to get started. And he talks a lot about Horner and a number of these other guys that you talk about as well.
Yeah.
That's part of why I was like, oh, look at that. So if you're interested, again, I'll have a link for the dynamics of lift and the drag and the XFLR5. So that way, if you want to kind of play around with your own, chord and get it helps you make your own coefficient of lift graphs and all of those graphs that we talked about in the aerodynamic lift stuff and the stuff we talked about here.
Yeah.
That way you can kind of play around and get your own handle on what you might want to design. Go and do that stuff.
Absolutely. XFLR5 is a lot of fun playing with it. I mean, it's endless, changing the thickness and where the maximum thickness has and where the camber happens and maximum camber. And I know we're getting close to the end here. It also has a method so that you can basically do a spline, so you can move dots around and just design your own airfoil just by moving the shape, so it smooths for you, and then you can tell it, okay,
cool.
go tell me what this will do. That's pretty
What
cool.
is that going to do? Yeah, pretty cool.
It's really good if you want to modify an airfoil a little bit. So you put the airfoil down on there, and then you can say, move the spline around so it fits exactly, and then you can make slight adjustments and start playing with it and move things. For example, one of the things that on the UAK2 airfoil is you'll notice that it's got a lot of curvature up near the nose. There's just a big arc there. And it took us a long time of playing around to try to figure out that gives you great lift and low coefficient of moment, moving that arc way up front. And it's just playing around with it, learn that.
Yeah. Nice.
And then another thing, sorry.
No,
one last thing about it.
Yeah,
another thing I learned from Horner is on airfoils kind of in the Reynolds number range that ultralights fly, the more round you make the nose, the broader that stall shape is on the coefficient of lift.
Okay.
Up to a point. If it's really sharp, it's going to be a sharp drop off curve. If you make it bigger around, it'll be a flatter, more rounded fall off on that stall.
Yeah. Really cool. I honestly just kind of going through it with what we presented in the aerodynamics and which is going off of a lot of what you presented in your courses or your not courses, but your videos. They really kind of helped me go, oh, and then add to that the Barnaby.
Barnaby wing fan,
Barnaby wing fans wing
airfoil selection.
Airfoil selection book.
Yeah.
Kind of he just kind of like, look, if you do this, it does this to the graph. If you do this, it does this to the graph. It does this. You do this is what happens. And you're like, oh. And so like, again, all these things kind of add together where you talk about what Raymer has in his book, the things you talk about in your in your videos, and then what kind of that description that Wayne Finn has in his book, and you're like, oh, now it's finally starting to all click. Holy cow, that took forever.
the one thing that
it was good.
I don't know if Barnaby said it, but you have your three measurements: your coefficient of lift, your coefficient of moment, and coefficient of drag.
Yep.
You can have two of them.
Yeah.
You can't have all three of those. Great. It just won't happen. You can get two of them pretty good. You can get one fantastic.
Right. You're trying to figure out which one's the most important to hone in on, and then see which one of the others are you like, well, I'm willing to sacrifice this.
Exactly. Yeah.
It depends on what your goal is. And that comes down to almost all the designs start with. And even RC. I mean, when we're looking at when I was designing the Kate, I had a design mission. There were certain parameters I wanted it to do, the things I wanted it to have capacity for, and that design mission informed the rest of those choices.
Mhm.
Maybe I wasn't doing all of those choices with regard to the airfoils, but there were choices. I did make a highly undercambered outer section, and it was a big section, and that was because I wanted to be slow and draggy, but I wanted to have high lift so it could just hang out. And it worked really well. So pretty cool. Again, doing basically that curve that you showed, that curved thin airfoil is essentially what the whole outer third of the wings are. So it's pretty cool. Very cool. I really appreciate your time, Leon, so much.
Well, thanks for inviting me. It's been fantastic.
Thank you. Joe, do you feel like taking us out, or?
Yeah, I can. Leon, thanks again. We'll just say
Sure.
100 times. It always is always special to us when somebody's willing to come on and spend their valuable time. You put in some incredible effort into the research and giving the knowledge. So thank you so much for that.
You're very welcome.
All right. Well, guys, as always, listen, you have enjoyed listening to this episode as much as the three of us have enjoyed sitting here talking and having our minds blown. Feel free to reach out to us. You can meet us in our Discord server. It'll be down in the doobly-doo. Thank you, Matthew Colville. You can reach out to us, Aviationrcnoob at gmail.com. You can reach Matthew at Aviationrcnoob.com, or you can reach me, Joe, at Aviationrcnoob.com. Feel free to swing by the Facebook group, not page, though we do still have some guys hanging out on the page. We got the website, Aviationrcnoob.com. I know Matt's got some potential big plans for that. We'll see what comes about of that in the next several months. We might actually do something with it. And
getting some work. We're getting some work figured out on it.
Yep, you've got build nights and build weekends throughout Build-January coming up.
Join me.
Join him, hang it. Even if you're not participating, come give Matt some company. He gets lonely. And keep your ears open. I promise in the near future I'll be doing a sim. I just got to get my stuff together and actually do it. But soon, trademark, reserve, copyright.
Oh, wow.
Matthew.
You went for all the things.
If there's nothing else.
No, not for me. Leon, you?
I'm good.
All right, guys. Thank you, and we will see y'all next time.
Bye.
Bye.
Part of what spurred on last episode. And hold on, I don't know if you can see, but I've got a cat in the background who's trying to take everything down.
My wife's cat will probably show up here shortly. You'll see a tail go across the camera.
Oh, it's just Ghost. I never hit record on the video.
Let's start over.
Okay, that's fine.
I'm so sorry.
I'm glad you caught it now rather than 20 minutes in.
Yeah.
Do you want to basically restart the audio, or we'll just know it's somewhere around 20 minutes or so?
We can just keep going.
Okay. Let me know when you're actually.
Now we're recording video. Leon, I am so sorry.
No problem. Well, you can just put the Noob's slide up there for the start. So that's
first
fine.
20 minutes.
Just kidding. Do you want to say something now about it as you start recording?
All right. Well, you're going to restart, so you do the whole thing, right?
Well, I'm sure that Matthew will take that opportunity for B-roll material.
Okay. If we can.
Okay, so
episode, we did a bit of a dry run the week before, going. She's asleep.
Oh, dreaming?
Oh yeah.
Must
Good
be.
times.
I don't know what that was. The